What if you could outrun a bullet? Not just any bullet, one traveling faster than the speed of light itself. Out there in the vast, silent expanse of space, objects move at velocities so extreme they defy everything we know about speed. Stars hurtling through galaxies like cosmic misfits, jets of energy blasting from black holes with enough force to rip through reality. These aren't just ideas from science fiction. They're real, they're happening right now, and they're rewriting the rules of physics as we speak. Picture this, a single star, flung from its home galaxy by the sheer gravitational might of a supermassive black hole, racing through the void at millions of miles per hour. It's not just fast, it's unstoppable, and that's just one of the universe's many speed demons. From rogue planets drifting between stars to beams of plasma screaming across space at nearly the speed of light, the cosmos is packed with objects that make even the fastest human-made machines look like they're standing still. But how? What cosmic forces could possibly accelerate something to these unimaginable speeds? And what happens when matter moves so fast it bends the very fabric of space and time? That's exactly what we're about to uncover. Over the next few minutes, we'll dive into 50 mind-blowing facts about the fastest objects in the universe, phenomena so extreme they challenge our understanding of reality itself. Whether it's hypervelocity stars escaping their galaxies or quasars firing energy across billions of light years, each of these cosmic speedsters has a story that'll leave you in awe. So buckle up, because we're about to take a ride through the universe's most extreme speed zones. Most stars follow the gentle rhythm of their galaxies, drifting in predictable orbits, but not hypervelocity stars. These cosmic renegades tear through space at unimaginable speeds, some exceeding 1,000 kilometers per second. How does a star even reach such velocities? The answer lies in the gravitational chaos around supermassive black holes. Picture two stars locked in orbit around each other, drifting too close to a black hole's edge. In a violent game of celestial pinball, one star gets captured by the black hole's pull, while the other is slingshotted outward at breakneck speed, flung across the galaxy like a stone from a sling. Take S5HVS1, for example, a hypervelocity star discovered racing through space at 1,700 kilometers per second. At that speed, it could travel from Earth to the Moon in just under 7 minutes. But what makes this star even more extraordinary? Its trajectory suggests it was ejected from the heart of the Milky Way, likely after a close encounter with Sagittarius, a star, our galaxy's own supermassive black hole. These rogue stars don't just move fast, they carry secrets about the extreme environments that launched them. By studying their paths, astronomers can trace them back to the very black holes that sent them hurtling into the void. And here's the wildest part. Hypervelocity stars aren't just fleeing their home galaxies, some are on a path to escape the pull of the cosmos altogether. With enough speed, they'll become true interstellar nomads, drifting forever through the darkness between galaxies. Imagine that, a star born in the crowded heart of a galaxy, now destined to wander the cosmic abyss alone. It's a reminder that even in the vastness of space, a single gravitational encounter can change an object's fate forever. Now imagine a cosmic lighthouse spinning so fast its surface moves at nearly a quarter the speed of light. Meet pulsar J1748-2446AD, the fastest spinning pulsar ever discovered, whirling 716 times every second. At that rate, it could complete Earth's entire day's worth of rotations in less than 2 minutes. The physics behind this dizzying speed is just as astonishing as the numbers themselves. Pulsars are neutron stars, the collapsed cores of dead massive stars packed so tightly that a teaspoon of their material would weigh billions of tons. When these stellar corpses form, they inherit the original star's angular momentum but shrink to a fraction of their former size. Like an ice skater pulling in their arms to spin faster, this conservation of momentum causes the neutron star to rotate at ludicrous speeds. But pulsar J1748 takes this phenomenon to extremes. At its equator, the surface streaks through space at 24% light speed, so fast that if it spun any quicker, centrifugal forces would rip it apart. What keeps these cosmic tops from self-destructing? Their incomprehensible density creates gravity 100 billion times stronger than Earth's, holding them together against their own violent rotation. Yet even these extreme conditions can't prevent some mind-bending side effects. The pulsar's magnetic field, trillions of times more powerful than our planet's, whips charged particles into beams that sweep across space like a celestial strobe light. Each rotation sends a pulse of radiation blasting past Earth patterns so precise they rival atomic clocks. These spinning marvels aren't just curiosities, they're cosmic laboratories. By studying them, scientists test Einstein's theory of relativity under conditions no lab could ever replicate. Gravitational waves ripple from their imperfections, space-time warps around their mass, and their surfaces hotter than the sun's core hint at states of matter that defy conventional physics. pulsar J1748 isn't merely breaking speed records, it's pushing the boundaries of how we understand the universe's fundamental laws. And somewhere out there, an even faster spinner might be waiting to rewrite the rules again. Black holes aren't just cosmic vacuum cleaners, they're also the universe's most powerful particle accelerators. Take the supermassive black hole at the center of galaxy M87, famous for its relativistic jet, a narrow beam of plasma screaming outward at 99% the speed of light. That's not just fast, it's physics pushed to the breaking point. These jets aren't random ejections, they're precision engineered by the black hole's extreme gravity and rotation. Picture the chaotic environment near the event horizon, where space itself is dragged into a swirling vortex by the black hole's spin, a phenomenon called frame dragging. Magnetic fields twist into coils tighter than a tornado, funneling superheated plasma into jets along the black hole's rotational axis. The particles in these jets don't just move quickly, they're catapulted with energies that dwarf anything produced in human-made colliders. A single proton in M87's jet can carry as much kinetic energy as a baseball hurled at 60 miles per hour, all from a single subatomic particle. What's truly mind-bending is how these jets defy time itself. At such ludicrous speeds, Einstein's relativity comes into play. Time for the particles in the jet slows dramatically compared to the rest of the universe. To an outside observer, the jet's plasma appears to crawl, even though it's moving at nearly light speed, a cosmic illusion caused by extreme velocity. Meanwhile, the jet's own perspective flips the script. From its viewpoint, the surrounding universe ages millennia in what feels like seconds. M87's jet stretches for 5,000 light-years, a searing scar across the cosmos visible even to amateur telescopes. But here's the kicker, we're seeing it as it was 55 million years ago when the light first began its journey toward Earth. That means this jet has been racing through space since the age of the dinosaurs, outrunning time itself. And it's not alone. Across the universe, supermassive black holes fire these relativistic jets like cosmic artillery, shaping galaxies and seeding the space between them with raw energy. They're proof that even the darkest objects in creation can unleash the brightest, fastest phenomena we've ever witnessed. Somewhere in the vast emptiness of space, a single proton once streaked toward Earth with such staggering energy that it defied all expectations. This wasn't just any cosmic ray, it was the "oh my god" particle screaming through the atmosphere at 99.9999999999% the speed of light. To put that into perspective, if you could somehow race alongside it, this tiny speck of matter was moving so fast that, from its point of view, the entire history of our planet would pass in less than a blink. The energy packed into that lone proton was mind-boggling, equivalent to a baseball hurtling at 100 kilometers per hour, squeezed into a particle a million billion times smaller. How does something so small carry such monumental force? The answer lies in the most violent corners of the cosmos. Unlike the hypervelocity stars or pulsars we've explored, these particles don't come from black holes or spinning stellar corpses. They're likely launched by unimaginably powerful shockwaves from supernova explosions or the chaotic jets of active galactic nuclei. But even then, no known cosmic event fully explains the oh my god particle's extreme energy. Here's where it gets even stranger. When such a high-energy particle slams into Earth's atmosphere, it triggers an explosive cascade of secondary particles, a subatomic fireworks show scientists call an air shower. The oh my god particle's impact in 1991 unleashed billions of these secondary particles, spreading over kilometers as they rained down. Yet despite decades of searching, we've only detected a handful of particles with comparable energy. That rarity makes them even more puzzling. Are they flukes of nature, or do they hint at undiscovered cosmic accelerators lurking in deep space? The real mystery isn't just their speed, it's where they come from. Unlike light, which travels in straight lines, cosmic rays are charged particles, meaning magnetic fields twist their paths into impossible-to-trace spirals. By the time they reach us, their origins are scrambled, leaving astronomers to play detective with cosmic breadcrumbs. Some theories point to quasar lightning, massive discharges of energy from the centers of distant galaxies. Others suggest these particles might be relics from the Big Bang itself, hurled across time and space. One thing's certain, each of these ultra-high-energy cosmic rays carries a message from the most extreme environments in existence. They're not just breaking speed records, they're pushing the limits of known physics, forcing scientists to question whether Einstein's century-old cosmic speed limit might have exceptions. And somewhere out there, another oh my god particle might be racing toward us right now, ready to challenge our understanding of the universe once again. Imagine a black hole so massive it could swallow our solar system whole. Now picture that same cosmic titan hurtling through space at 7.5 million kilometers per hour. That's exactly what astronomers witnessed with 3C-186. A supermassive black hole ejected from its galaxy like a cosmic cannonball. This isn't just a leisurely drift through the cosmos. It's a full-blown escape with enough force to leave a 200,000 light-year-long trail of glowing gas in its wake, a celestial skid mark etched across the universe. How does something with billions of times the sun's mass get flung into the void? The answer lies in the chaotic ballet of colliding galaxies. When two galaxies merge, their central black holes eventually spiral toward each other, locked in a gravitational dance. As they draw closer, they emit ripples in space-time called gravitational waves. If their masses or spins aren't perfectly balanced, the final merger can kick the newly formed black hole in one direction, launching it at speeds that defy logic. Think of it like a slingshot with the recoil of a billion supernovas. 3C-186 didn't just get a gentle nudge, it was catapulted with such force that it escaped its host galaxy entirely. But here's where it gets stranger. The black hole didn't leave quietly. As it plowed through intergalactic gas, it dragged its own accretion disk, a swirling vortex of superheated material, along for the ride. This disk, glowing brighter than entire galaxies, now stretches behind the black hole like a cosmic jet stream, visible across cosmic distances. The sheer energy of this displacement ionizes the surrounding gas, lighting up the void like a neon sign in the darkness. What's truly staggering is the scale of this phenomenon. The black hole's speed is so extreme that if it were in our solar system, it could travel from Earth to Neptune in just 14 minutes. And it's not alone. Astronomers have spotted other runaway black holes with similar velocity, each one a testament to the universe's capacity for violence on a scale we can barely comprehend. These renegades challenge our assumptions about how black holes behave, proving that even the most massive objects in existence aren't anchored in place when the cosmos decides to throw them across the void. The implications ripple far beyond a single black hole's journey. These events could explain why some galaxies appear to be missing their central black holes entirely. They were literally kicked out of their homes. Others might carry the scars of such ejections in the form of distorted spiral arms or unusually bright gas trails. And for smaller galaxies, a passing supermassive black hole could spell disaster, tearing through star systems and disrupting the delicate balance of gravity that holds everything together. Perhaps most fascinating of all is what happens next. A black hole moving this fast isn't just escaping its galaxy, it's on a one-way trip into the emptiness between galaxies where it may drift for eternity. Without new material to feed on, its glowing trail will eventually fade, leaving it invisible in the darkness. But for now, 3C186 serves as a breathtaking reminder. Even the mightiest forces in the universe are subject to the chaos of cosmic collisions. And somewhere out there, another black hole might be gearing up for its own interstellar getaway. Gamma-ray bursts are the universe's ultimate power surges, violent eruptions of energy that outshine entire galaxies for a few fleeting seconds. But their true speed isn't just in their brightness, it's in the jets they fire across the cosmos. These narrow beams of radiation and particles rip through space at 99.9999% the speed of light, a velocity so extreme it creates illusions that defy common sense. Take the record-shattering gamma-ray burst known as GRB 221009A, detected in 2022. Its jets didn't just move fast, they warped our perception of speed itself. Here's the mind-bending part. Material in these jets can appear to move faster than light from our perspective, even though nothing technically breaks Einstein's cosmic speed limit. This illusion, called superluminal motion, happens when a jet points almost directly at Earth. The particles are racing toward us at near light speed while emitting light, meaning each new photon has less distance to travel than the one before it. The result, a cosmic mirage where the jet's material seems to outpace its own light. Imagine a runner on a treadmill sprinting toward you while the belt rolls backward. If they're fast enough, their forward progress still appears exaggerated from your viewpoint. That's exactly how gamma-ray bursts trick our telescopes. GRB 221009 wasn't just notable for its speed. It was the brightest gamma-ray burst ever recorded, flooding detectors with so much energy that astronomers initially thought it must be a malfunction. Later analysis revealed its jets traveled 7.5 billion light-years before reaching us, yet their intensity rivaled celestial objects in our own cosmic backyard. The sheer power required for such extreme speeds and luminosity suggests an apocalyptic origin, likely a supermassive star collapsing directly into a black hole, funneling its death throes into twin particle beams. Relativistic effects make these jets even stranger. Time dilation slows the burst's internal clock from our perspective, stretching seconds into hours. Meanwhile, the jet's own light gets compressed into higher frequencies through Doppler shifting, transforming invisible radio waves into deadly gamma rays. This is why gamma-ray bursts can be seen across the universe. Their light gets a cosmic boost from their unimaginable velocity. But the real mystery lies in what accelerates them to these extremes. Current theories point to magnetic fields trillions of times stronger than Earth's, coiled like springs around newborn black holes. When these fields snap, they catapult particles with energies 1,000,000 times beyond what our most powerful colliders can produce. Some jets even show evidence of internal shocks, collisions between fast-moving material within the beam itself, creating cascades of particles that glow across the electromagnetic spectrum. GRB 221009A's jets left another clue in their wake, a faint afterglow that faded over weeks. By studying this lingering light, astronomers reconstructed the jet's structure like forensic scientists analyzing a cosmic crime scene. They found it wasn't a smooth beam but a turbulent filament threaded with knots of ultra-dense plasma, proof that even at near light speed, matter behaves in complex, unpredictable ways. These bursts aren't just curiosities, they're natural laboratories for physics we can't replicate on Earth. Their jets create conditions where quantum effects and gravity collide, where particles reach energies that might unlock secrets about dark matter or extra dimensions. And with every new detection, we're reminded that the universe's speed limits aren't just numbers. They're boundaries waiting to be tested by nature's most extreme experiments. Meet S4714, the fastest star we've ever found, whipping around our galaxy's central black hole at a staggering 24,000 kilometers per second. That's 8% the speed of light, fast enough to cross the entire United States in less time than it takes to blink. But raw velocity isn't even the most shocking part of this star's story. Its orbit is a cosmic roller coaster, a dizzying, lopsided loop that swings it closer to Sagittarius, a star, than any other known star before violently slinging it outward again. Picture an egg-shaped path so extreme that at its closest approach, S4714 skims a mere 12 billion miles from the black hole's event horizon, roughly the distance from our Sun to Pluto's orbit. At that range, gravitational forces stretch and compress the star like taffy, heating its surface to temperatures that would vaporize steel. Yet somehow, it survives each perilous pass, completing a full orbit in just 7.6 years. Compare that to our solar system's leisurely 230 million-year stroll around the Milky Way, and you start to grasp the sheer audacity of this stellar speedster's path. The secret to S4714's breakneck pace lies in Kepler's laws of planetary motion, the same rules that govern Earth's orbit, cranked up to cosmic extremes. Just as a comet accelerates when nearing the Sun, this star gains phenomenal speed as it falls toward Sagittarius, a star's crushing gravity well. At Astron, its closest approach, it's moving 30 times faster than when it's farthest out. The numbers defy intuition. In mere months, it transitions from slow orbital speed, still 20 times Earth's solar velocity, to a flash of light so fast its own photons get stretched into infrared by relativistic effects. Astronomers didn't just stumble upon this record breaker. Detecting S4714 required 17 years of painstaking observations using adaptive optics to cut through the galactic core's dust clouds. Even then, its existence was only confirmed by tracing subtle shifts in position across hundreds of high-resolution images, like picking out a single firefly's path in a stadium of flashing lights. The effort paid off, revealing a star whose orbit serves as a precision tool for measuring Sagittarius, a star's mass, with unprecedented accuracy. But the real surprise: S4714 shouldn't exist. Conventional models predict stars this close to a supermassive black hole should be torn apart by tidal forces or collide with other objects in the densely packed galactic center. Its survival hints at either an incredibly dense composition or an origin story as wild as its orbit. Some theorists suggest it might be the remnant of a binary star system, one partner torn away by the black hole's gravity while the other was catapulted into this extreme trajectory. Others propose it formed farther out and migrated inward through chaotic gravitational interactions. What's certain is that every close pass leaves its mark. S4714's light carries telltale signatures of extreme gravitational redshift, a stretching of wavelengths as photons struggle to escape the black hole's pull. This effect, predicted by Einstein but rarely observed so dramatically, lets scientists test general relativity under conditions once thought impossible to study. Meanwhile, the star's repeated brushes with oblivion may be seeding the surrounding space with stripped material, feeding the faint glow of accretion processes around Sagittarius, a star itself. Future observations could reveal even faster stars skirting closer to the black hole's edge, perhaps even one destined for a final, fatal plunge. For now, S4714 stands as a testament to nature's ability to push celestial mechanics to their breaking point. It's a reminder that even in the ordered dance of orbits, the universe reserves space for daredevil stellar rebels racing through gravity's gauntlet with no guarantee they'll survive another lap. Quasars aren't just the brightest beacons in the universe. They're also cosmic engines capable of launching gas at speeds so violent they can alter the fate of entire galaxies. Picture a supermassive black hole, billions of times heavier than our Sun, devouring matter with such ferocity that it glows brighter than 1,000 Milky Ways. But here's the twist: not everything that falls toward this monster gets swallowed. Some gas is hurled back into space at 20% the speed of light, forming supersonic winds powerful enough to strip galaxies of their star-forming fuel. These quasar outflows aren't gentle breezes, they're tsunamis of energy. Take the quasar SDSSJ 1106+1938, whose winds were clocked at 26,000 kilometers per second. At that speed, gas could cross the distance from Earth to the Sun in under 2 hours. The force behind this acceleration is mind-bending. Radiation pressure from the quasar's intense light pushes particles outward, while magnetic fields twist and channel them into focused streams. The result, a hurricane of charged particles so energetic it can blow a galaxy's gas reservoir clean into intergalactic space. What makes these outflows even more astonishing is their scale. A single quasar can launch this high-speed gas across hundreds of thousands of light-years far beyond its host galaxy's borders. Astronomers call this quasar feedback, and it's one of the universe's most dramatic examples of a black hole shaping its surroundings. Without these outflows, galaxies would grow unchecked, forming stars until they exhausted their gas. But quasars act like cosmic regulators, their winds shutting down star formation by literally sweeping the galactic floor clean. Evidence for this comes from so-called red and dead galaxies, massive, ancient systems brimming with old stars but devoid of new ones. Their quiet, gas-free states suggest they once hosted quasars whose furious winds drained them of star-making material billions of years ago. It's a cosmic irony. The same black holes that power the universe's brightest objects also have the power to strangle their own galaxy's growth. Yet quasars don't just destroy, they create too. By heating and redistributing gas, their outflows can trigger new star formation in surrounding regions, like a forest fire clearing the way for fresh growth. Some theories even suggest these winds helped seed the universe with heavy elements, spreading material forged in the quasar's furnace across intergalactic space. The legacy of quasar outflows is written across cosmic time. Without them, galaxies might look radically different, denser, brighter, and far more chaotic. Instead, these high-speed winds impose order, sculpting the universe into the balanced structures we see today. They're proof that even the most destructive forces in nature can be architects of cosmic evolution, their influence echoing billions of years after the quasars themselves have faded to darkness. When a massive star dies, it doesn't just fade quietly into the cosmic night. It goes out with a bang so violent it can fling stellar corpses across the galaxy. Neutron star kicks are one of the universe's most extreme examples of celestial recoil, where the explosive death throes of a supernova launch these ultra-dense remnants at speeds that defy imagination. Take the Guitar Nebula pulsar, racing through interstellar space at 1,600 kilometers per second. So fast it's carving a sonic boom through the cosmos in the form of a glowing, guitar-shaped shockwave. The physics behind these stellar catapults is as fascinating as their speed. During a supernova, the collapsing core of a massive star doesn't always explode symmetrically. If more material gets ejected in one direction than another, the conservation of momentum slingshots the newborn neutron star in the opposite direction, like a cannon firing backward. But this isn't just a gentle nudge. The forces involved are so immense they can accelerate a city-sized object weighing more than our Sun to velocities that would cross the Atlantic Ocean in under 3 seconds. What makes the Guitar Nebula pulsar so striking isn't just its speed, it's the spectacular wake it leaves behind. As the pulsar plows through interstellar gas at hypersonic speeds, it creates a bow shock, a glowing arc of compressed particles heated to millions of degrees. The nebula's distinctive shape comes from the pulsar's rapid motion combined with its powerful magnetic field, which funnels particles into twin jets that trail behind it like cosmic guitar strings strummed by the void itself. This glowing trail stretches over 15 light-years, a cosmic breadcrumb marking the pulsar's path through the galaxy. But how do we know these neutron stars got kicked rather than born with this velocity? The smoking gun lies in their trajectories. Many, like the pulsar B1508+55, are moving so fast they'll eventually escape the Milky Way entirely, their speeds far exceeding the galaxy's gravitational pull. By tracing their paths backward, astronomers can often pinpoint the supernova remnants where they originated, sometimes revealing a ghostly shell of expanding gas with no neutron star at its center, only a trail leading toward some distant point in the cosmos. The energy behind these kicks is staggering. To launch a neutron star at 1,600 kilometers per second requires the equivalent of 10 quadrillion nuclear bombs detonating in perfect unison. Yet despite this violence, the neutron star itself remains intact, a testament to the incomprehensible density that allows these objects to withstand forces that would vaporize anything else. Their survival raises an even more intriguing question. Could some of these high-velocity remnants be carrying planets with them? Theoretical models suggest it's possible. A neutron star's gravitational grip is so strong that any surviving planetary bodies from its pre-supernova system might get dragged along for the ride. Imagine a frozen, irradiated world orbiting a pulsar, hurtling through the galaxy at a fraction of light speed, a cosmic hitchhiker on the universe's fastest road trip. While we haven't confirmed such systems yet, the possibility adds another layer of wonder to these stellar speed demons. What's perhaps most remarkable is how neutron star kicks shape the galaxy's ecology. These runaway pulsars distribute heavy elements forged in supernova far from their birthplaces, seeding the interstellar medium with material for future stars and planets. Their high-speed journeys also mean they're not confined to the galactic disk. Some may be racing through the halo or even beyond, carrying a piece of the Milky Way's history into intergalactic space. The Guitar Nebula pulsar won't play its cosmic song forever. As it continues its high-velocity journey, the interstellar medium will gradually slow it down over millions of years, but not before it's traveled hundreds of light-years from its explosive birth. For now, it remains a stunning example of how stellar death can create some of the universe's fastest objects, proving that even in destruction, the cosmos finds ways to set new speed records. And somewhere out there, another supernova may be preparing to launch its own neutron star on an epic, high-speed voyage across the galaxy. Locked in a gravitational death spiral, two white dwarfs in the Cancri system are rewriting the rules of orbital speed. These stellar remnants whip around each other at 1.8 million kilometers per hour, so fast they complete an entire orbit in just 5.4 minutes. To put that in perspective, in the time it takes to brew a cup of coffee, these cosmic partners could circle one another more than 10 times. What makes this binary system truly extraordinary isn't just the speed, it's the relentless physics that force them closer together with each passing second. The secret behind Cancri's breakneck dance lies in Einstein's century-old prediction, gravitational waves. As the white dwarfs orbit, they distort the fabric of space-time itself, sending out ripples that carry energy away from the system. This loss causes their orbits to shrink by nearly 1 meter every day, a slow-motion collapse that's gradually accelerating their spin to even more extreme velocities. Imagine two skaters holding hands and spinning faster as they pull their arms in, except in this case, the arms are the invisible tendrils of space-time curvature binding them together. Detecting this system required unprecedented precision. Astronomers first noticed Cancri as a flickering X-ray source blinking with clockwork regularity. Further observations revealed the truth: not a single object, but two Earth-sized stars made of crystallized carbon and oxygen, separated by just 1/3 the distance from Earth to the Moon. Their proximity creates staggering tidal forces. If you stood on one, ignoring the crushing surface gravity, the other would dominate the sky like a monstrous, glowing disk stretching from horizon to horizon. The future of this system is even more dramatic. Current models suggest that in roughly 300,000 years, a blink in cosmic terms, the white dwarfs will merge, potentially triggering a supernova explosion or collapsing into a neutron star. But until then, they serve as a natural laboratory for testing general relativity under conditions no Earth experiment could replicate. The precise timing of their orbits, detectable down to millisecond variations, offers one of the cleanest measurements of gravitational wave effects ever observed. What's perhaps most surprising is that Cancri isn't alone. Several ultra-fast binary systems have since been discovered, each pushing the limits of orbital mechanics. But none match the sheer velocity of these white dwarfs, a record that may stand until we find two neutron stars dancing even closer to the brink of collision. For now, Cancri remains the universe's premier example of how gravity, given the right conditions, can transform a quiet stellar afterlife into the most frenetic orbital race imaginable. Drifting through the void between galaxies, colossal rivers of hydrogen race toward the Milky Way at speeds that defy simple explanation. The Smith Cloud, a behemoth stretching 11,000 light-years long and 2,500 light-years wide, is barreling toward our galaxy at 300 kilometers per second, fast enough to cross the distance from Earth to the Moon in just 13 minutes. But this isn't some passive interstellar weather pattern. It's a high-velocity fossil carrying clues to one of the universe's most dramatic events, a violent collision between galaxies billions of years ago. What makes hypervelocity clouds like the Smith Cloud so extraordinary isn't just their speed, it's their improbable survival. Intergalactic space is a brutal environment where sparse gas should have long since dissipated such structures. Yet here they are, barreling through the cosmos with enough mass to form 2 million suns. The secret lies in their magnetic scaffolding, invisible fields that act like cosmic rubber bands, holding these hydrogen streams together across millions of light years. Without them, the Smith Cloud would have unraveled like smoke in the wind before ever reaching us. Tracing these clouds back to their origins is like galactic detective work. The Smith Cloud's trajectory points toward the constellation Aquila, but its true birthplace lies far beyond. Chemical fingerprints reveal it didn't form in the Milky Way's pristine outer halo. Its metal content is too high. Instead, astronomers believe it was torn from another galaxy during an ancient close encounter, perhaps the long-ago collision that formed the Virgo stellar stream. That cataclysm likely flung the cloud outward at incredible speed, only to have gravity eventually pull it back toward our galactic disk. Right now, the Smith Cloud is on a return collision course. In roughly 30 million years, it will smash into the Milky Way's spiral arms like a cosmic tidal wave, triggering fireworks of star formation where its hydrogen slams into denser galactic gas. This won't be the cloud's first impact. Its leading edge already shows signs of turbulence as it plows through our galaxy's outer atmosphere. But the main event will dwarf anything we've witnessed, potentially delivering enough fresh fuel to birth entire clusters of new stars. What's truly remarkable is how common these hypervelocity clouds might be. Recent radio telescope surveys suggest the Milky Way is surrounded by dozens of similar structures, some falling inward, others speeding away like intergalactic escapees. Each one tells a different chapter in our galaxy's violent history of mergers and close encounters. Together, they form a dynamic ecosystem of high-speed gas flows that continually reshape galactic chemistry, redistributing the raw materials for future stars across cosmic time. The Smith Cloud may seem distant and slow-moving on human timescales, but it's a stark reminder that galaxies aren't static islands. they're dynamic creatures, constantly exchanging matter with their surroundings through these high-velocity rivers. Long after our sun burns out, this cosmic delivery of intergalactic hydrogen will keep the Milky Way's star factories running, proving that even the emptiest regions of space can harbor the fastest, most unexpected travelers. At first glance, Velocity seems to break the universe's ultimate speed limit. Its jets appear to race across space faster than light itself. But this cosmic magic trick, known as superluminal motion, isn't a violation of physics. It's a breathtaking illusion born from relativistic geometry. Here's how it works. When a jet of plasma streaks toward Earth at nearly light speed, the time delay between emitted photons gets compressed. Imagine a cosmic treadmill where each step forward brings the runner closer to the finish line. Photons released later have less distance to travel, so they arrive almost on the heels of earlier ones. From our perspective, this creates the impossible illusion that the jet's material is outpacing its own light. The math behind this is as elegant as it is mind-bending. If a jet travels at 99% light speed and points just 5 degrees away from our line of sight, simple trigonometry makes its apparent motion across the sky seem 7 times faster than light. Velocity's jets exploit this effect perfectly. Their tight angle toward Earth combines with near-light speed velocity to produce apparent speeds up to 9 times the cosmic limit. It's like watching a plane fly directly toward you. Even at cruising speed, its position against distant mountains seems to shift almost imperceptibly. But tilt that same plane slightly, and suddenly its motion becomes dramatically visible. What seals the illusion is time dilation. The jet's internal clock runs slower from our vantage point due to relativistic effects, making its real speed appear even more exaggerated. Meanwhile, Doppler boosting brightens the approaching side of the jet while dimming the receding side, another clue that we're witnessing a cosmic sleight of hand rather than true faster-than-light travel. Radio astronomers first spotted this phenomenon in the 1970s while tracking blazars like Velocity, their observations revealing knot-like structures in jets that seem to separate at impossible speeds. The real beauty lies in what superluminal motion reveals about these jets. By measuring apparent speeds from different angles, astronomers can calculate true velocities and even map the intricate spiraling paths of particles within the beam. Some jets show multiple knots moving at varying apparent speeds, evidence of shock waves rippling through the plasma at slightly different orientations. Others display gradual acceleration patterns, hinting at magnetic fields that focus and propel particles over millions of years. This illusion isn't just a curiosity, it's a vital tool for probing the universe's most energetic environments. Without it, we'd severely underestimate the power of active galaxies and quasars, mistaking their relativistic jets for slower, less energetic outflows. It also serves as a natural test of Einstein's relativity. If anything truly moved faster than light relative to its local space-time, the illusion would shatter. Yet century after century, observations confirm that superluminal motion remains just that, a spectacular trick of perspective, reminding us that in the cosmos, even speed has layers of deception. PSR J0952-0607 isn't just another cosmic record breaker. It's a neutron star spinning so fast its equator streaks through space at 70,000 kilometers per second. That's nearly 1/4 the speed of light, a velocity where the laws of physics start to warp under extreme centrifugal forces. Clocking in at 707 rotations every second, this pulsar's surface completes a full spin in less time than it takes a hummingbird to flap its wings once. But what makes this object truly extraordinary isn't just its dizzying speed. It's how it teeters on the knife's edge of destruction, pushing neutron star physics to its absolute limits. The story of this cosmic top begins with its formation. Like all neutron stars, PSRJ 0952-0607 was born from the violent collapse of a massive star's core during a supernova explosion. But unlike slower spinning pulsars, this one gained an extra rotational kick, likely from cannibalizing a companion star's material. As gas spiraled onto its surface, the transfer of angular momentum revved it up like a cosmic spinning wheel, accelerating it to speeds that defy intuition. Now it's so fast that if it were any larger or spun any quicker, the outward centrifugal force would overcome its own gravity, ripping it apart in a catastrophic explosion. Surviving at this speed requires incomprehensible density. The pulsar packs roughly 1.4 times the Sun's mass into a sphere no wider than Manhattan, creating gravity 100 billion times stronger than Earth. This crushing force is the only reason its surface doesn't fly off into space. Every atom there weighs as much as a battleship, locked in place by a gravitational vice grip. Yet even this can't fully counteract the rotational strain. Precise measurements reveal the star isn't perfectly spherical. Its equator bulges outward slightly, stretched by the relentless spin like a cosmic pizza dough mid-toss. What's truly fascinating is how PSRJ 0952-0607 tests our understanding of matter itself. The pressures at its core are so extreme that protons and electrons merge into neutrons, forming a superfluid, a bizarre state of matter that flows without friction. Some theories suggest the core might contain even stranger particles like free-floating quarks or hyperons, whose properties could rewrite nuclear physics textbooks. Meanwhile, its crust, a crystalline lattice of atomic nuclei, is under such titanic stress that it regularly fractures, sending starquakes rippling across the surface in seismic waves detectable as subtle changes in rotation speed. Astronomers discovered this pulsar not by its light, but by the rhythmic pulses of radio waves it emits like a lighthouse beacon. Each rotation beams radiation across space, timed so precisely that over decades, the accumulated delay would amount to less than a millisecond. This precision makes it a natural laboratory for relativity. As the pulsar spins, frame dragging, a distortion of space-time predicted by Einstein causes its orbit to wobble in ways that let scientists measure the star's internal structure indirectly. Even its faint gravitational waves, rippling outward at the rotation frequency, carry clues about how matter behaves under conditions impossible to recreate on Earth. The future of this cosmic speed demon holds even more mysteries. Current models suggest it's gradually slowing down as it radiates energy, but the rate is agonizingly slow, losing just one rotation per second every 8 million years. Yet in its prime, PSRJ 0952-0607 may have been even faster, perhaps briefly crossing the theoretical limit where neutron stars can no longer hold together. If astronomers ever find a pulsar spinning beyond this breakup speed, it would force a radical rethink of how matter behaves under extreme conditions. Until then, this record holder remains a testament to nature's ability to push celestial mechanics to the very brink and leave us marveling at the universe's capacity for extremes. Some stars don't just die, they get fired into the void like cosmic cannonballs. Supernova remnant J0617 is racing through intergalactic space at 3,000 kilometers per second, fast enough to cross the entire United States in just over 1 second. What makes this celestial runaway extraordinary isn't just its speed, it's the glowing, comet-like tail stretching 16 light-years behind it, a shimmering scar marking its violent expulsion from its home galaxy. This isn't your typical supernova aftermath. Most stellar explosions leave behind debris that lingers near their birthplaces, slowly mixing with surrounding gas. But J0617 defies the norm. It's a solitary traveler, already hundreds of thousands of light-years from any visible galaxy. The secret to its extreme velocity lies in a cosmic quirk of stellar physics, asymmetric explosions. When the original star detonated, its core likely collapsed off-center, creating a lopsided blast that kicked the remnant like a rocket misfiring. Combine that with gravitational slingshots from passing stars or dark matter clumps, and you've got a recipe for intergalactic escape. The remnant's glowing tail tells a story of brutal interstellar friction. As J0617 plows through the sparse gas between galaxies at hypersonic speeds, it compresses and heats the material in its path, creating a shockwave that glows in X-rays, a cosmic version of the sonic boom from a supersonic jet. Meanwhile, heavier elements forged in the supernova, like iron and silicon, get smeared across intergalactic space like a celestial paintbrush, enriching regions that might one day form new stars and planets. Astronomers first spotted this intergalactic traveler by its unusual radio signature, a combination of pulsar-like emissions and an elongated gas trail unlike anything seen in galactic supernova remnants. Follow-up observations revealed an even stranger detail. Its motion is too fast to have originated in any nearby galaxy we've identified. This raises the tantalizing possibility that J0617 might have been ejected from an invisible dwarf galaxy or even a rogue stellar cluster drifting between galaxies. The implications ripple far beyond one runaway remnant. If intergalactic supernovae are common, they could explain mysteries like the abundance of heavy elements in the cosmic voids, regions once assumed to be pristine hydrogen deserts. These high-speed ejecta act as galactic pollinators, spreading the raw materials for rocky planets across unimaginable distances. Some theories even suggest that a significant fraction of the universe's neutron stars and black holes might be hurtling unseen through intergalactic space, ghosts of ancient stellar explosions that kicked them beyond their galaxy's gravitational grasp. Yet J0617 won't roam forever. Over millions of years, drag from intergalactic gas will gradually slow its furious flight. Eventually, it may be captured by another galaxy's gravity, adding its enriched remains to some distant future solar system. Until then, it serves as a stark reminder. Even in death, stars can achieve velocities that defy their galactic origins, seeding the cosmos with the remnants of their explosive final acts. Deep within the tangled remnants of supernova SN 1006 lies one of nature's most powerful particle accelerators, a shock wave ripping through space at 5,000 kilometers per second. This isn't just debris expanding from a stellar explosion. It's a high-energy physics laboratory on a cosmic scale where atoms get torn apart and rebuilt at velocities approaching light speed. What makes these relativistic shock waves extraordinary isn't their speed alone. It's how they transform ordinary space into a factory for cosmic rays, generating subatomic bullets with energies that dwarf anything produced in human-made colliders. The process begins when the supernova's blast wave slams into surrounding interstellar gas like a supersonic tsunami. The collision creates a boundary so violent that it separates charged particles from their electrons, ionizing the gas into a seething plasma. But here's where it gets wild. As protons and heavier nuclei cross this shock front, they get caught in a chaotic electromagnetic slingshot. Turbulent magnetic fields on either side of the shock act like cosmic ping-pong paddles, bouncing particles back and forth across the boundary, with each pass adding more energy. Some protons complete this frenzied loop hundreds of times before finally breaking free, now accelerated to nearly light speed. SN 1006's shock wave showcases this phenomenon with textbook clarity. Observations reveal twin arcs of X-ray emission tracing the shock's leading edge, where electrons spiral along magnetic field lines at relativistic speeds. But the real action happens just behind this visible boundary, in an invisible zone where protons get catapulted to energies 1,000,000 times beyond what the Large Hadron Collider can produce. These particles don't just zip off into space, many ricochet back into the shock region, creating a self-sustaining acceleration cycle that persists for centuries. The supernova's shock owes its longevity to an ingenious cosmic balancing act. As it expands, the wave continuously converts kinetic energy into particle acceleration rather than dissipating as heat. This allows it to maintain its breakneck speed across vast distances. SN 1006's shock front now stretches over 30 light-years while still moving fast enough to cross Earth's orbit in under 3 hours. The shock structure holds vital clues too. Its rippled surface suggests interactions with denser interstellar clouds, creating pockets where particle acceleration hits overdrive. These shock waves aren't just academic curiosities, they solve a century-old mystery about cosmic rays. Since their discovery in 1912, scientists struggled to explain how subatomic particles could reach such extreme energies naturally. SN 1006's shock provides the smoking gun, a natural accelerator mechanism powerful enough to produce the high-energy protons that constantly bombard Earth's atmosphere. Modern detectors have even traced some of these cosmic rays back to similar supernova remnants, confirming their role as galactic particle factories. The implications stretch far beyond one stellar explosion. Shock acceleration operates wherever supersonic flows collide, from the solar wind's interaction with planetary magnetospheres to the jets of active galaxies. Each environment tweaks the basic recipe. Some shocks generate mostly electrons, while others favor heavy nuclei. SN 1006 represents the middle ground, a balanced case where both light and heavy particles get boosted to extreme velocities. By studying its intricate shock dynamics, astronomers can decode the universal principles governing particle acceleration across the cosmos. What makes SN 1006 particularly special is its age. At just over 1,000 years old as seen from Earth, it captures the shock acceleration process at a perfect stage, old enough for the shock to have developed complex structure, yet young enough that its engine still runs at nearly full power. Over the next few millennia, as the shock plows through increasingly thin interstellar gas, its acceleration efficiency will gradually decline. But for now, it remains one of our clearest windows into how the universe transforms ordinary matter into the fastest, most energetic particles in existence. No multi-million-dollar laboratory required. Some planets endure extreme weather, but PSRJ 1311-3430b faces conditions that make mere storms look trivial. This is a world literally being vaporized by its own sun. Orbiting a pulsar every 93 minutes at 2.5 million kilometers per hour, this lava and metal sphere holds the record for fastest known exoplanet, completing a full year in less time than it takes to watch a movie. Imagine a world where gravity is so intense that a teaspoon of its surface material would weigh as much as an elephant, all while radiation blasts strip away its atmosphere atom by atom. The pulsar anchoring this cosmic demolition derby isn't just any dead star. It's a millisecond pulsar spinning 600 times per second with beams of X-rays and gamma rays powerful enough to sterilize planets light years away. Every orbit, this hellish world plunges through that death beam, heating its surface to temperatures hotter than many stars. The radiation pressure is so intense that astronomers can actually detect the planet's evaporating gases trailing behind it like a comet's tail, a 20 billion kilometer-long stream of ionized metal vapor torn from its surface at nearly 1% light speed. What's truly astonishing is how this planet even exists. Pulsars form when massive stars collapse in supernova, explosions violent enough to obliterate any nearby worlds. Yet PSRJ 1311-3430b somehow survived, likely as the charred core of a gas giant whose outer layers were ripped away in the cataclysm. Now it's essentially the skeleton of a planet, a dense ball of crystalline carbon and heavy metals being slowly dismantled by its undead sun. The discovery story reads like a cosmic detective thriller. Astronomers first noticed the pulsar's gamma-ray pulses had slight, regular dimming clues that something was periodically blocking the beams. After ruling out instrument errors, they realized the only explanation was an orbiting body so close it completes a lap in the time it takes to microwave popcorn. Further observations revealed the planet's evaporative tail through subtle distortions in the pulsar's radio emissions, like spotting a candle's flicker next to a floodlight. This planetary extreme athlete isn't just breaking records. It's teaching us about survival in the universe's most hostile environments. The same radiation eroding it also creates bizarre chemical reactions in its remaining atmosphere, potentially forging mineral clouds of corundum and periclase, gemstones raining through skies hotter than lava. And its existence proves planets can form from the ashes of stellar explosions, hinting at unseen worlds hugging other pulsars in our galaxy. Yet PSRJ 1311-3430b's days are numbered. At its current evaporation rate, models suggest it will be completely disintegrated within a few 100 million years, a blink in cosmic time. Until then, it serves as a stark reminder that the universe doesn't just harbor fast objects, it creates entire worlds living on borrowed time, dancing at the edge of annihilation. Nestled in the chaotic heart of our galaxy, the S-stars perform a deadly cosmic ballet around Sagittarius, a star, their orbits tracing wild, lopsided ellipses that bring them terrifyingly close to the supermassive black hole's event horizon. These stellar daredevils aren't just fast, they're gravitational gymnasts, with some like S2 hitting speeds over 5,000 kilometers per second during their closest approaches. That's fast enough to cross the continental United States in under 1 second, a velocity so extreme it warps the very light these stars emit. What makes the S-stars cluster so extraordinary isn't merely their speed, it's how they survive the black hole's tidal forces at such close range. During its nearest pass, S2 streaks just 17 light hours from Sagittarius, a star's event horizon, about 3 times the distance from our Sun to Pluto. At that proximity, gravity stretches the star like taffy, its outer layers pulled into a glowing stream of superheated plasma. Yet astonishingly, it holds together, completing its chaotic 16-year orbit intact. Scientists credit its survival to an incredibly dense core and rapid rotation, a cosmic spin that helps counteract the black hole's disruptive forces. The S-stars' orbits serve as celestial stopwatches for testing Einstein's theories. As S2 swings past the black hole, its light stretches into longer, redder wavelengths, an effect called gravitational redshift predicted by general relativity. The star's path also precesses, gradually rotating like a spirograph drawing with each orbit. This subtle drift, precisely measured over decades, confirms space-time around Sagittarius, a star, isn't just curved. It's being dragged around by the black hole's rotation like honey swirling around a spoon. But how did these stars get so close to certain doom in the first place? Their youth poses a particular puzzle. Many S-stars are surprisingly young, just a few million years old, while the brutal environment near a supermassive black hole should prevent star formation entirely. One theory suggests they migrated inward after forming farther out, caught in a gravitational tug of war with other dense objects. Another posits they were born in situ from compressed gas disks somehow stable enough to collapse despite the black hole's ferocious tides. Their chemical fingerprints, rich in heavy elements, hint at violent origins, possibly as the surviving cores of shredded binary star systems. The cluster's dynamics also reveal hidden secrets about Sagittarius, a star itself. By tracking S-star orbits, astronomers calculated the black hole's mass with unprecedented precision, equivalent to 4 million suns packed into a space smaller than our solar system. These measurements even uncovered mysterious G-objects, dusty stellar hybrids that behave like stars when distant but stretch into gas clouds when nearing the black hole. Some may be merged stars cloaked in veils of debris, offering clues about the chaotic mergers happening in this extreme environment. Yet the S-star's greatest spectacle comes during their closest approaches, where relativity's effects crescendo. At peak velocity, time for these stars slows dramatically compared to the outer galaxy. An observer near Sagittarius, a star, would see S2's orbit complete slightly faster than we do from Earth. Meanwhile, the black hole's gravity bends the star's light into asymmetrical arcs, creating bizarre visual distortions that challenge astronomers' models. These moments provide rare glimpses into how matter behaves under gravity's most extreme conditions, data that could reshape our understanding of physics itself. What's unfolding here isn't just a display of cosmic speed. It's a grand experiment written in starlight, one that may eventually reveal whether Einstein's theories hold near a black hole's edge or if new physics emerges in these extreme regimes. And somewhere in that frenzied stellar dance, another S-star might be preparing for its own blistering close approach, ready to push our knowledge of gravity, motion, and spacetime to even greater extremes. When two neutron stars collide, they don't just merge. They detonate in a cataclysm so violent it can fling stellar debris outward at nearly 1/3 the speed of light. These kilonova explosions are cosmic forges, where the universe's heaviest elements, gold, platinum, uranium, are born in the chaos of rapid neutron capture and then hurled across space at speeds that defy imagination. Picture a single cloud of freshly minted gold, blasted into the void faster than any human spacecraft could ever hope to travel, carrying the spoils of a stellar collision that outshines entire galaxies for days. The physics behind these extreme ejections begins with the neutron star's ludicrous density. Each one packs more mass than our Sun into a sphere no wider than a city, creating gravitational tides so strong they distort spacetime itself as they spiral toward collision. When they finally merge, the outer layers get shredded into a swirling, superheated disk of neutrons and protons, a nuclear pressure cooker where atoms are crushed and rebuilt in microseconds. But the real fireworks start when magnetic fields and neutrinos launch shockwaves through this debris, accelerating portions of it to relativistic speeds in opposing jets. The result, a rapidly expanding shell of heavy elements propelled by forces that make hydrogen bombs look like firecrackers. GW170817, the first kilonova detected with both gravitational waves and light, offered a front-row seat to this process. Observations revealed its ejecta racing outward at 30% light speed, fast enough to cross the distance from Earth to Neptune in just under an hour. The afterglow's spectrum told an even more astonishing story. Fingerprints of newly synthesized gold and platinum weighing more than our entire planet, vaporized into a glowing fog. That single event alone may have produced over 200 Earth masses of precious metals, scattering them through the cosmos at velocities that could carry them clear across galactic distances. What's truly staggering is how these extreme speeds shape the aftermath. The fastest-moving material punches through interstellar gas like buckshot, creating bow shocks that glow in X-rays for years. Slower clumps, rich in uranium and thorium, leave radioactive trails that decay over centuries, cosmic breadcrumbs for astronomers to follow. And because kilonovae are relatively rare, occurring maybe once every 100,000 years per galaxy, each one's ejecta becomes a time capsule, preserving the conditions of its violent birth for millennia. The implications rewrite our understanding of cosmic chemistry. Before kilonovae were confirmed as heavy element factories, scientists assumed supernova produced all the universe's gold. But the math never quite added up. Supernova lacked the neutron-rich environment needed to forge such dense atoms efficiently. Kilonova ejecta, with their breakneck speeds and perfect nuclear conditions, solve the mystery. They're proof that the universe's most valuable elements aren't just made in explosions, they're literally thrown across space like gems from a shattered vault. Even more mind-bending, some of that gold might be here with us now. Simulations suggest our solar system formed in a region possibly seeded by one or more nearby kilonovae billions of years ago. The wedding ring on your finger or the circuitry in your phone could contain atoms forged in a neutron star collision and delivered at relativistic speeds long before Earth even existed. It's a humbling thought every precious metal on our planet may have begun its journey as stellar shrapnel from one of the universe's most extreme and high-speed events. Yet the story doesn't end there. The fastest ejecta from these mergers don't just carry heavy elements, they also transport our process nucleosynthesis's secrets, offering clues about neutron star interiors we can't replicate in any lab. By tracking their velocities and compositions, scientists can reverse engineer the extreme conditions during the merger itself. Some models even suggest the speediest material might contain exotic nuclear isomers or super-heavy elements that decay before reaching us, their fleeting existence etched into the ejecta's expansion patterns. As for where these cosmic bullets end up, the fastest clouds could eventually escape their host galaxies altogether, enriching the barren voids between them with precious metals. Others might collide with molecular clouds, sparking new star formation with a ready-made supply of heavy elements for future planets. And somewhere out there, another neutron star binary is inching toward its own cataclysmic merger, ready to launch another wave of hyperfast cosmic treasure into the darkness. ESO 137-001 isn't just another spiral galaxy. It's a cosmic speedster racing through the Norma cluster at 7 million kilometers per hour, shedding stars and gas like sparks from a firework. This isn't a gentle drift through space. It's a full-blown demolition derby where the galaxy's delicate spiral arms are being torn apart by the sheer force of intergalactic wind. The result, a 260,000 light-year long tail of displaced material enough to stretch from our Milky Way to its nearest galactic neighbor and back twice over. What makes this galaxy's breakneck journey so extraordinary is the invisible obstacle course it's navigating. The space between galaxies in a cluster isn't empty, it's filled with superheated gas, sometimes called the intracluster medium. This plasma is thin by Earth standards, but at ESO 137-001's velocity, it might as well be concrete. As the galaxy plows through, the pressure strips away its interstellar gas like tissue paper in a hurricane. X-ray telescopes reveal the aftermath, a shimmering wake of multi-million-degree gas glowing behind the galaxy, mixed with tendrils of cooler hydrogen dragged violently from its disk. The real tragedy unfolds in the tail. This isn't just stray gas, it's the raw material for future stars ripped from the galaxy's grasp. Under normal conditions, that gas would have condensed into glittering new star clusters. Instead, it's being scattered across intergalactic space, leaving the galaxy itself to slowly starve. Observations show the tail is peppered with orphaned star-forming regions, pockets where stripped gas managed to collapse before dispersing entirely. These doomed stellar nurseries burn brightly for now, but without their parent galaxy's structure, they'll eventually fade into the cluster's haze. Yet ESO 137-001's ordeal offers astronomers something rare, a real-time lab for studying galactic evolution. Most stripping processes take billions of years, but here we're witnessing it unfold on cosmic fast-forward. The galaxy's remaining spiral structure reveals how different components respond. Dust lanes vanish first, followed by diffuse hydrogen, while denser molecular clouds cling longer. Even the galaxy's magnetic fields leave ghostly imprints in the tail, detectable through polarized radio emissions. The galaxy's speed isn't just destructive, it's transformative. As it loses gas, its ability to form new stars dwindles, condemning it to become a lenticular or elliptical galaxy over time. This might explain why galaxy clusters are dominated by such shapes, not because they formed that way, but because the cluster environment literally sandblasts them into new forms. ESO 137-001 is a snapshot of this metamorphosis caught mid-transformation. But there's a twist in this galactic tragedy. Some of that stripped material doesn't just vanish, it enriches the cluster. Heavy elements forged in the galaxy's stars now mingle with the intracluster medium, seeding future generations of galaxies with ready-made ingredients for planets and life. In a sense, ESO 137-001 sacrifice feeds the cosmic cycle, its loss becoming another system's gain. The galaxy's fate is sealed. It will continue shedding mass until only its core remains, a ghost of its former spiral glory. Yet even in its demise, it reveals the brutal beauty of the cosmos, a universe where speed isn't just about motion, but transformation, where entire galaxies can be reshaped by the invisible currents of intergalactic space. And somewhere out there, another spiral might be entering its own high-speed trial by fire, ready to paint the darkness with its own luminous streak of stellar debris. Quasar winds don't just blow, they scream across the cosmos at velocities so extreme they reshape galaxies like cosmic hurricanes. Among the fastest are ultra-fast outflows, superheated gas jets racing outward at 40% the speed of light, so powerful they can strip entire galaxy clusters of their star-forming fuel. These aren't mere gusts, they're titanic forces unleashed by supermassive black holes feasting on matter, converting swallowed gas into energy so intense it overpowers gravity itself. Take the quasar PDS 456, whose outflow was clocked at 46,000 kilometers per second. At that speed, a single atom in this wind could circle Earth's equator 7 times in 1 second. The energy behind this is incomprehensible every second. These outflows carry away the equivalent of 10 suns worth of mass in raw kinetic energy. But what makes them truly transformative isn't their speed alone, it's their reach. Unlike the focused jets we've explored earlier, ultra-fast outflows spray in wide cones, flooding surrounding space with enough force to heat interstellar gas across millions of light-years. This creates a paradoxical effect. The same black holes that devour matter also act as cosmic regulators, their winds preventing galaxies from growing too large too fast. The mechanics behind these outflows reveal nature's ingenuity. As material spirals toward a quasar's central black hole, friction heats it to millions of degrees, creating a pressure cooker of ionized plasma. Magnetic fields channel some of this superheated gas outward, while radiation pressure, the sheer force of light particles colliding with matter, launches it like a cosmic slingshot. The result is a multiphase wind, dense clumps of gas embedded in a faster, thinner medium, all rushing outward with enough momentum to displace entire nebulas. Evidence of their impact is etched across galaxy clusters like SC 0627-54, where X-ray telescopes reveal vast cavities carved by ancient quasar winds. These bubbles, now filled with ultra-fast outflow remnants, act as galactic fingerprints, proof of outbursts that occurred billions of years ago. The timing is critical. Many astronomers believe these eruptions explain why the most massive galaxies stopped forming stars early in cosmic history. Their winds essentially blew out the galactic furnace, starving future generations of stars before they could ignite. Yet these outflows aren't purely destructive. By heating gas without fully ejecting it, they create conditions where star formation resumes in controlled bursts rather than chaotic starbursts. Some models even suggest they prevent galaxies from overfeeding their central black holes, a self-regulating mechanism that maintains equilibrium across cosmic time. It's a delicate balance. Too much wind and galaxies wither, too little and they'd choke on their own unchecked growth, the most fascinating aspect. These winds might be universal. While quasars power the fastest outflows, even quieter galaxies show evidence of scaled-down versions, hinting that black holes of all sizes influence their surroundings through similar processes. From dwarf galaxies to sprawling clusters, ultra-fast outflows represent one of the cosmos' most overlooked architects, silent, invisible, yet capable of shaping the universe as profoundly as gravity itself. And as telescopes probe deeper into space, we're finding these winds might be more common and more influential than we ever imagined. some of the universe's fastest objects are the ones running away from their own violent past. Pulsar B2224+65 isn't just hurtling through space at 1,600 kilometers per second, it's carving an interstellar masterpiece behind it. This cosmic fugitive leaves a glowing trail stretching 5 light-years, shaped like a perfectly straight gun barrel, forged from pure physics where the pulsar's incredible speed meets the delicate gas between stars. The secret behind this celestial bullet's speed lies in its explosive birth. When its progenitor star went supernova, the collapse wasn't symmetrical, more material blasted outward in one direction than the others. Like a rocket experiencing uneven thrust, the newborn pulsar got kicked in the opposite direction with enough force to send it racing across the galaxy. Now it moves so fast that if it were passing through our solar system, it could travel from Earth to Pluto in just 10 days. What makes this pulsar truly spectacular isn't just its velocity, it's the shockwave it creates. As B2224+65 plows through interstellar hydrogen at supersonic speeds, it compresses the gas ahead like snow piling against a plow. The resulting shock heats the gas to millions of degrees, causing it to glow in X-rays. Meanwhile, the pulsar's powerful magnetic field channels charged particles into twin beams along its axis, creating that eerie gun barrel shape. From certain angles, it looks like the universe itself lined up the perfect shot. Astronomers first noticed this intergalactic marksman through its radio pulses, rapid, precise bursts that revealed its rapid spin despite its even more impressive translational speed. But the real surprise came when optical telescopes caught its glowing trail. Most pulsar tails curve or twist as they interact with uneven interstellar material. But B2224+65's wake is unnaturally straight, suggesting it's moving through an unusually uniform region of space, or that its speed is so great it simply overpowers any minor density variations in its path. The pulsar's breakneck journey raises a fascinating question. Where is it headed? Tracing its path backward suggests an origin in the Cygnus constellation, perhaps born from a massive star in the famous Cygnus OB2 association. Its current trajectory, however, puts it on an escape course from the Milky Way entirely. Within a few 100 million years, it will likely become an intergalactic wanderer, its gun barrel trail fading as it leaves the galaxy's gas-rich disk behind. Yet even as it flees, B2224+65 offers scientists invaluable data. The temperature and structure of its shockwave provide clues about the interstellar medium's density, while the pulsar's motion helps map the Milky Way's gravitational field. Its rapid spin, despite its age, hints at complex magnetic field interactions that may be slowing its rotation less than standard models predict. Every detail adds another piece to the puzzle of how these stellar remnants interact with their surroundings after their violent births. What's most astonishing is that this pulsar isn't unique, just exceptionally well-angled for observation. The galaxy likely harbors hundreds of similar runaway neutron stars, many with even more spectacular trails we can't currently see. Some might be moving faster, their paths curved by encounters with massive objects we've yet to map. Others could be generating particle beams visible only in gamma rays or leaving wakes in dark matter rather than gas. Each one tells a story of cosmic violence and stellar escape, written in the language of light and magnetic fields. B2224+65 serves as a reminder that in the cosmos, destruction and creation often go hand in hand. The same explosion that birthed this pulsar also enriched the galaxy with heavy elements, while its flight continues to reshape the interstellar medium in its path. Even as it speeds toward intergalactic oblivion, it leaves behind both beauty and knowledge, a fleeting masterpiece etched across the stars. Most failed stars drift through space as cold, listless orbs, but not two MASS J0348-6022. This cosmic overachiever spins so fast it completes a full rotation every 1.08 hours. its equator racing at over 100 kilometers per second. That's not just quick for a brown dwarf, it's teetering on the edge of physical possibility, rotating at nearly 90% of the speed where centrifugal force would rip it apart. What makes this speed demon extraordinary isn't just its velocity, it's how a celestial object this cool can muster such extreme motion. Brown dwarfs occupy the awkward gap between planets and stars, too small to ignite hydrogen fusion but larger than gas giants. Without a star's internal heat to drive atmospheric circulation, most become sluggish rotators. Yet 2MASSJ0348 defies expectations, spinning faster than any known brown dwarf while barely heating above 800 degrees Celsius, cool enough that if you could stand on its cloud tops ignoring the crushing gravity, the sunset would cycle every 54 minutes as different atmospheric bands whip into view. The secret to its speed lies in a youth spent gathering momentum. Like an ice skater pulling in their arms, brown dwarfs spin faster as they age and contract. But this one appears to have hit the cosmic jackpot, either forming from an exceptionally fast rotating gas clump or receiving an angular momentum boost from a long-gone companion object. Now it's essentially a failed star behaving like a pulsar, with weather systems and magnetic fields struggling to keep up with the dizzying rotation. Observing this rapid spin required ingenious detective work. Astronomers monitored subtle shifts in its light spectrum caused by Doppler effects, one side of the brown dwarf rotating toward us while the other recedes. The data revealed equatorial speeds approaching the theoretical breakup limit for an object of its mass and density. At these velocities, the centrifugal force stretches the dwarf into an oblate shape, wider at the equator than the poles, like a cosmic spinning top deformed by its own motion. The implications challenge our understanding of substellar atmospheres. At such speeds, Coriolis forces should dominate weather patterns, potentially creating jet streams and storm systems unlike anything seen on slower brown dwarfs. Some models suggest the rapid rotation might even generate auroras thousands of times brighter than Earth's, as charged particles spiral along distorted magnetic field lines. Then there's the mystery of why it hasn't slowed down. Most brown dwarfs gradually lose angular momentum through winds and magnetic braking. 2MASSJ0348's stubborn refusal to decelerate hints at unknown mechanisms preserving its spin against all odds. This speedster also offers clues about planetary formation. If giant planets can achieve similar rotation rates, and some hot Jupiters come close, their atmospheres might exhibit equally extreme dynamics. Future telescopes could search for similar ultra-fast rotators among exoplanets, testing how universal these rotational extremes really are. For now, 2MASSJ0348 remains a solitary marvel, a cosmic underachiever that became record-breaker, spinning perilously close to the edge of stability while rewriting the rules for substellar objects. Rising like colossal balloons from the Milky Way's core, the Fermi bubbles stretch 50,000 light-years, towering structures of ultra-hot gas racing outward at 3 million kilometers per hour. These aren't gentle expansions, they're the scars of an ancient cataclysm, a volcanic eruption on galactic scales where our supermassive black hole, Sagittarius A star, once belched enough energy to dwarf a billion supernova. The bubble's sheer velocity defies logic. Their leading edges move fast enough to cross the distance from Earth to the Moon in less than half a second, propelled by forces we're only beginning to understand. What makes these outflows especially puzzling is their origin story. Unlike the focused jets seen in active galaxies, the Fermi bubbles represent a more explosive event, likely a frenzied feeding episode where Sagittarius A star devoured an entire gas cloud or star cluster millions of years ago. The resulting energy didn't channel into narrow beams but erupted in a spherical shockwave, punching through the Milky Way's dense central regions like a cosmic pressure cooker blowing its lid. X-ray and gamma-ray telescopes reveal the aftermath, a pair of faintly glowing structures filled with turbulent gas, their surfaces crackling with magnetic fields and peppered with high-energy particles. Yet speed isn't the bubbles' only mystery. Their pristine chemical composition, lacking the heavy elements typical of star-forming regions, suggests they originated directly from the black hole's surroundings rather than mixed galactic material. This pristine gas acts like a fossil record, preserving conditions near Sagittarius, a star before the eruption. Even more intriguing are the cap regions at their tops, where the outflow collides with intergalactic gas, creating shock fronts detectable across the electromagnetic spectrum. These interfaces serve as natural particle accelerators, generating cosmic rays with energies beyond anything achievable in human-built colliders. The bubble's discovery in 2010 by the Fermi Gamma Ray Space Telescope revolutionized our view of the galactic center. Prior to this, astronomers assumed Sagittarius, a star, had been dormant for eons. The bubbles proved otherwise, revealing that our black hole, though quiet now, was once an engine of unimaginable violence. Their symmetrical shape suggests the eruption was brief by cosmic standards, perhaps lasting just 100,000 years. But its legacy endures in the form of these gargantuan, high-speed structures. Connecting this ancient outburst to present-day observations opens new questions. Faint X-ray filaments threading the bubbles resemble sonic booms frozen in gas, marking where the outflow plowed through denser galactic material. Meanwhile, maps of polarized radio waves reveal a vast magnetic scaffold, suggesting fields played a crucial role in shaping the explosion. Some theories even propose the event was triggered by a close encounter with a dwarf galaxy, its gas destabilizing the delicate balance at the Milky Way's core. For all their grandeur, the Fermi bubbles are fleeting by cosmic standards. Over millions of years, their gas will gradually mix with the Milky Way's halo, dispersing their energy and metals. But for now, they stand as towering monuments to our galaxy's volatile past, proof that even seemingly quiet black holes can awaken with devastating force, launching hypervelocity storms that reshape their surroundings for epochs to come. And hidden in their faint glow might be clues to when and how violently Sagittarius, a star, might erupt again. Locked in a gravitational tango at over 1 million kilometers per hour, the binary pulsar system PSR J0737-3039 isn't just breaking speed records, it's rewriting our understanding of space-time itself. This cosmic duo consists of two neutron stars separated by just 800,000 kilometers, closer than the distance from Earth to the Moon, racing through their orbits every 2.4 hours with such precision they could replace atomic clocks. What makes this system extraordinary isn't merely its velocity, but how these ultra-dense stellar corpses serve as nature's premier laboratory for testing Einstein's general relativity under conditions no Earth experiment could ever replicate. The dance between these pulsars reveals space-time's curvature in stunning detail. As they spiral toward each other, their immense gravity distorts the fabric of reality, emitting gravitational waves that carry energy away from the system. This causes their orbits to shrink by 7 millimeters per day, a minuscule change that would be imperceptible in most systems, but here is measurable with breathtaking accuracy thanks to the pulsar's clock-like radio pulses. Each neutron star's rotation acts as a cosmic lighthouse, beaming radiation toward Earth with such regularity that deviations as small as millionths of a second can be detected, exposing subtle relativistic effects. One of the system's most groundbreaking revelations involves the Shapiro time delay, a phenomenon where a pulsar's signals slow slightly as they pass through its companion's gravitational field. In PSR J0737-3039, this effect is so pronounced it allows scientists to map the warping of space around the second neutron star with unprecedented precision, confirming Einstein's predictions down to a fraction of a percent. Then there's the geodetic precession, a wobble in the pulsar's spin axes caused by their motion through curved space-time, visible as gradual changes in the pulse shapes over years of observation. Yet the real showstopper is how this system demonstrates gravitational damping. Unlike the single pulsars we've explored earlier, this binary pair's mutual orbit provides direct evidence that gravitational waves exist exactly as relativity predicts. Their orbital decay matches theoretical calculations so precisely that it earned the system's discoverers the 2003 Nobel Prize in Physics, cementing neutron star binaries as gold standard tests for fundamental physics. What's truly astonishing is how these pulsars maintain their extreme velocities despite the energy they're losing. Each neutron star weighs 500,000 times more than Earth, yet fits within a sphere smaller than Manhattan, creating surface gravities so strong that if you dropped a marshmallow from 1 meter above, it would impact with the energy of a nuclear bomb. Their proximity means tidal forces are constantly reshaping them, perhaps creating internal fractures that release bursts of X-rays or alter their spin rates in detectable ways. The future of this cosmic partnership holds even more revelations. Within 85 million years, a blink in cosmic time, the two pulsars will collide in a kilonova explosion, an event that will ripple space-time with gravitational waves detectable across the universe. Until then, their relentless spiral continues, offering new tests of relativity, from frame-dragging effects to potential deviations that might hint at new physics beyond Einstein's theory. Other relativistic binaries have since been discovered, but none match the precision of this original pair, a celestial metronome keeping perfect time to the rhythm of curved space-time. For astronomers, PSR J0737-3039 represents more than just a cosmic oddity. It's a natural ultra-high-precision instrument that has already transformed our understanding of gravity. Each pulse from these neutron stars carries information about the universe's fundamental forces, proving that sometimes the most extreme objects make the most reliable measuring sticks. And as they continue their high-speed waltz toward destruction, they remind us that even in death, stars can illuminate the deepest secrets of physics. Most stellar survivors fade quietly into the cosmic background, but not LP40-365. This white dwarf is barreling through the Milky Way at 3.5 million kilometers per hour, a speed so extreme it could cross the entire United States in under 2 seconds. What makes this stellar remnant truly remarkable isn't just its velocity, it's the violent origin story written in its chemical fingerprint. This isn't a typical white dwarf cooling into oblivion. It's the shrapnel from a supernova explosion that somehow didn't fully destroy it, a cosmic phoenix that endured one of the universe's most catastrophic events only to be flung across the galaxy like a celestial bullet. The secret to LP40-365's survival lies in its bizarre composition. Unlike normal white dwarfs, which are primarily carbon and oxygen, this rogue fragment contains startling amounts of neon, magnesium, and heavier metals. These elements are the smoking gun of a Type Ia supernova, the thermonuclear detonation of a white dwarf that's gorged on material from a companion star. Normally, these explosions leave nothing behind, but LP40-365 suggests a tantalizing alternative. Sometimes the blast can be lopsided, kicking a chunk of the original star clear of the devastation while the rest vaporizes. Imagine the forces required to accomplish this. The supernova's shockwave had to propel this fragment fast enough to escape its own expanding debris field, a velocity surpassing the star system's orbital speed around the galaxy. The energy involved is staggering, equivalent to detonating every nuclear weapon on Earth simultaneously and focusing all that force onto a single city-sized object. Yet against all odds, LP40-365 endured, becoming one of the only known white dwarfs with a visible velocity vector pointing directly away from a known supernova remnant. The aftermath is written in its trajectory. Tracing its path backward leads astronomers toward the constellation Ursa Major, where models suggest it began its journey around 50 million years ago. The white dwarf's current speed is so great that the Milky Way's gravity can't bend its path into a typical orbit. Instead, it's on a hyperbolic escape trajectory, destined to become an intergalactic wanderer. Along the way, its surface tells a story of violence. Spectroscopic analysis reveals layers alternately enriched and depleted by the supernova's turbulent mixing, like geological strata recording a stellar-scale earthquake. What's truly groundbreaking is how this survivor challenges supernova models. Until its discovery, astronomers assumed Type I explosions were symmetrical, leaving no remnants. LP40-365 proves that under the right conditions, perhaps asymmetric ignition or magnetic field configurations, white dwarfs can partially survive their own destruction. This opens the door to a potential new class of objects, supernova crumbs scattered across the cosmos, each carrying clues about the precise mechanics of stellar detonations. The implications stretch beyond astrophysical curiosity. Type I supernova serve as cosmic distance markers, their predictable brightness helping map the universe's expansion. If some leave behind fragments like LP40-365, their luminosity calculations might need adjustment, a small but crucial detail for precision cosmology. Meanwhile, the white dwarf's composition offers a rare sample of supernova-processed material, allowing scientists to study nucleosynthesis products without waiting for debris clouds to disperse. Right now, this stellar fugitive continues its high-speed flight through the galactic halo, outshining normal white dwarfs by a factor of 100 thanks to residual heat from its traumatic birth. In a few million years, it will cool and fade, but for now, it remains a blazing testament to nature's ability to defy expectations, proving that even in total annihilation, some remnants can be launched toward extraordinary new destinies. Galaxies aren't just islands of stars, they're dynamic engines breathing life into the cosmos through winds powerful enough to reshape entire regions of space. Take starburst galaxy M82, where supernova explosions and young, massive stars combine to launch gales of superheated gas at over 2 million kilometers per hour, fast enough to cross the solar system in under a day. These aren't gentle breezes, they're tsunamis of energy capable of lifting entire nebulas clear of the galaxy's disk, creating the fiery filaments visible in Hubble images as glowing red tendrils stretching 40,000 light-years into intergalactic space. What makes M82's winds so transformative is their cargo. As the gas surges outward, it carries heavy elements forged in stellar cores: oxygen, carbon, iron, scattering them far beyond where they originated. This galactic alchemy turns simple hydrogen clouds into reservoirs of planet-building material, enriching the cosmic environment for future generations of stars and solar systems. The numbers are staggering. Every year, M82's winds eject 10 times the Sun's mass worth of enriched material, equivalent to launching 1,000 Earths into the void annually. Over millions of years, this creates an invisible highway of metals spanning intergalactic distances, linking galaxies through shared chemical signatures. The physics behind these outflows reveals nature's intricate balance. Young, massive stars dozens of times heavier than our Sun, live fast and die young, exploding as supernova within mere millions of years. Their combined energy creates bubbles of hot gas that merge into continent-sized cavities beneath the galaxy's disk. When these pressurized regions rupture, they blast material outward like champagne corks popping from a shaken bottle. X-ray telescopes reveal the aftermath. Gas heated to millions of degrees streaming along magnetic field lines, while cooler molecular clouds get caught in the flow like leaves in a hurricane. M82 offers a nearby laboratory to study these processes with unmatched clarity. Most starburst galaxies exist billions of light-years away, but this one sits just 12 million light-years distant in Ursa Major, close enough for astronomers to resolve individual outflow structures. Observations show the winds accelerating as they climb from the galaxy's plane, reaching peak velocity where they escape the gravitational pull entirely. Yet there's a surprising twist. The fastest-moving material isn't smooth, but clumpy, with dense knots of gas surviving the journey intact. These cosmic survivors could eventually seed star formation in the most unexpected places, perhaps explaining why some stars are found drifting far between galaxies. The long-term impact of these winds transcends their home galaxy. By redistributing heavy elements, they fundamentally alter the chemistry of future star-forming regions. Computer simulations suggest that without such outflows, galaxies would retain all their metals, creating subsequent generations of stars with radically different compositions, and potentially altering the development of rocky planets like Earth. M82's winds represent just one thread in a cosmic web of chemical exchange, proving that galaxies aren't closed systems but participants in a grand, interconnected cycle of matter spanning the observable universe. Yet perhaps the most profound lesson comes from comparing M82 to our own Milky Way. Galactic archaeology reveals that our galaxy underwent similar starburst episodes billions of years ago, meaning the atoms in our bodies might trace back to ancient winds from long quiet stellar factories. Those same processes continue today in distant galaxies, invisibly weaving the elements of future worlds into the fabric of deep space. Every time we observe M82's fiery plumes, we're glimpsing the engine that built the universe as we know it, one high-speed particle at a time. In October 2017, astronomers spotted an interstellar vagabond racing through our solar system, an object so unusual it sparked debates that continue to this day. Oumuamua, the first confirmed visitor from another star system, wasn't just passing through, it was practically fleeing, accelerating away from the Sun at 315,000 kilometers per hour. That's fast enough to cross the Atlantic Ocean in under 20 seconds, a velocity so extreme it defied simple explanations. The more scientists studied this cosmic speedster, the stranger it became, a tumbling, cigar-shaped rock with no visible coma or tail, yet exhibiting subtle acceleration that couldn't be explained by gravity alone. Theories about Oumuamua's bizarre behavior range from the mundane to the extraordinary. On the natural end, some researchers propose it's a fragment of a Pluto-like exoplanet, blasted into space by an ancient collision and coated with nitrogen ice that sublimated in sunlight, creating a faint but measurable thrust. Others suggest it could be a hydrogen iceberg, an exotic object theorized to form in the coldest regions of interstellar space, where molecular hydrogen freezes solid. As sunlight warmed its surface, escaping hydrogen gas might have acted like a natural rocket engine, nudging it along its path. These explanations paint Oumuamua as a rare but naturally occurring cosmic relic, a frozen time capsule from another star's planetary formation process. But not everyone is convinced. The object's extreme elongation, estimated at up to 10 times longer than it was wide, along with its unusual brightness variations and lack of detectable outgassing, led some scientists to entertain more speculative ideas. Could it be a light sail from an alien civilization, drifting silently through space after completing its mission? While this hypothesis grabbed headlines, most astronomers remain skeptical, pointing out that extraordinary claims require extraordinary evidence. What's undeniable is that Oumuamua's speed and trajectory make it a statistical outlier. Calculations suggest our solar system should host thousands of similar interstellar objects at any given time, yet none had been detected before, and none since have matched its peculiar characteristics. The real puzzle lies in the acceleration. Comets speed up as ices boil off their surfaces, creating visible tails, but Oumuamua showed no such activity, even under intense scrutiny from the world's most powerful telescopes. Recent simulations suggest another possibility. Maybe it was venting buried gases through pores in its surface, creating thrust without the typical dusty plume. This would make it a new class of object, a dark comet with hidden reserves of volatile materials that only activate under stellar heating. If true, future surveys might uncover more of these stealthy travelers, rewriting our understanding of how planetary systems exchange material across the galaxy. Oumuamua's brief visit left more questions than answers, but its legacy endures. This mysterious speedster proved that interstellar objects can reach blistering velocities through natural processes, while simultaneously challenging astronomers to expand their definitions of what constitutes a comet or asteroid. By the time it passed Jupiter's orbit, already too faint to observe, it had cemented its place in history, not just as the first known interstellar visitor, but as a cosmic riddle that continues to provoke wonder and debate. Whether exotic artifact or natural oddity, one thing is certain: somewhere out there, more interstellar travelers are racing unseen through the void, each carrying secrets from distant stars. And the next one might be even stranger. Deep within the tangled wreckage of Cassiopeia A, electrons race through twisted magnetic fields at speeds so extreme they blur the line between matter and pure energy. This supernova remnant, the corpse of a star that exploded 300 years ago as seen from Earth, now acts as a natural particle accelerator, boosting electrons to 99.9999% the speed of light. At these velocities, a single charged particle could circle our planet 7 times in less than a second, carrying enough energy to power a city for minutes if we could harness it. The mechanism behind this acceleration is both elegant and violent. As the supernova's shockwave plows through interstellar space at 15,000 kilometers per second, it creates a turbulent frontier where magnetic fields tangle like cosmic spaghetti. Electrons caught in this chaos get trapped between converging shock fronts, ping-ponging back and forth across the boundary, with each pass injecting more energy. Picture a surfer riding an endless wave, but instead of water, the wave is a wall of ionized gas, and the surfer gains speed exponentially with every bounce until they're moving at nearly light speed. What makes Cassiopeia A's electrons particularly fascinating is how we detect them. Unlike slower particles, these relativistic electrons emit synchrotron radiation, a brilliant glow spanning radio to X-ray wavelengths as they spiral along magnetic field lines. The remnant's filamentary structure, visible in Chandra X-ray observatory images, acts like a giant particle track detector, revealing where the fastest electrons concentrate. Some regions shine with peculiar intensity, hinting at local magnetic knots where acceleration reaches overdrive, possibly due to collisions between the shockwave and denser interstellar clouds. These electrons aren't just breaking speed records, they're solving a century-old cosmic puzzle. Since the early 20th century, scientists have detected mysterious high-energy particles called cosmic rays bombarding Earth's atmosphere. Cassiopeia A provides the smoking gun that supernova remnants can produce such particles naturally. The electron's extreme energies match theoretical predictions for the first stages of cosmic ray acceleration, suggesting protons and heavier nuclei get similarly boosted in these environments. Some models indicate the shockwave's most energetic protons might reach even higher velocities than the electrons, though their neutral charge makes them harder to track directly. The real magic happens at the shock front's microscopic level. As electrons approach light speed, relativistic effects dramatically alter their behavior. Their mass effectively increases, requiring exponentially more energy for each incremental speed gain. The surrounding magnetic fields, meanwhile, become amplified by the electron's own motions, a feedback loop that further enhances acceleration. Quantum effects start playing unexpected roles too. Some electrons may briefly surf on plasma waves within the shock, gaining concentrated energy bursts that defy classical physics models. Cassiopeia A's electron factory won't run forever. Over millennia, the shockwave will gradually slow as it sweeps up more interstellar material, and the magnetic fields will weaken as the remnant expands. But for now, it serves as one of our clearest natural laboratories for studying particle acceleration at energies unreachable in human-built colliders. Every X-ray, photon, and radio wave we detect from this cosmic wreck carries encoded information about how the universe transforms ordinary matter into the fastest, most energetic particles in existence. No multi-million-dollar facility required. Perhaps most remarkably, this process isn't unique. Similar electron acceleration likely occurs in supernova remnants across the galaxy, each contributing to a vast pool of relativistic particles that permeate interstellar space. Some of these electrons may eventually escape into the cosmic void, where their synchrotron glow could one day illuminate other civilizations' telescopes. Others might get reaccelerated by later shocks, riding multiple supernova waves like cosmic hitchhikers on an endless highway of energy. As we piece together Cassiopeia's secrets, we're glimpsing a universal engine, one that has been converting stellar death into particle acceleration since the first stars exploded billions of years ago. These relativistic electrons are more than just cosmic speed demons. They're the sparks in a grand, galaxy-wide recycling process, turning destruction into the raw materials for future cosmic phenomena. And somewhere in that glowing wreckage, even faster particles might be hiding, waiting to challenge our understanding of physics' ultimate speed limit. Most black holes anchor their galaxies like cosmic pit bulls, but not XT Joan 118+480. This rogue singularity barrels through the Milky Way at 400 kilometers per second, fast enough to travel from New York to Los Angeles in roughly 10 seconds. What makes this celestial outlaw so fascinating isn't just its speed, it's the violent backstory that launched it into the galactic wilderness, a tale written in gravitational recoil and disrupted star clusters. Astronomers first spotted this black hole's presence not by seeing it directly impossible for these light-trapping monsters, but by its gravitational grip on a captive star. As the star orbits the invisible predator, its gas spirals inward, heating to millions of degrees and emitting telltale X-rays. Tracking this binary system's motion revealed something astonishing. The pair wasn't just drifting through the galaxy's disk like most stellar objects. It was streaking through space at nearly twice the speed of typical stars, leaving a trail of dynamical evidence pointing to a dramatic ejection event. The leading theory traces this black hole's origins to a densely packed globular cluster, one of those ancient spherical star cities orbiting the Milky Way. Here's how the cosmic escape likely unfolded. In the cluster's crowded core, a binary black hole system formed, their gravitational dance tightening over millennia. When a third black hole wandered too close, the ensuing three-body battle flung one participant clear at breakneck speed, a gravitational slingshot so powerful it overcame the cluster's pull entirely. XT Joan 118+480 became a galactic fugitive, its star companion the sole witness to its violent past. What makes this speed demon unique is its intermediate mass, roughly 6 times heavier than our Sun. That places it in a curious category between stellar mass black holes and supermassive giants, suggesting globular clusters might be hiding more of these middleweight outcasts. Its trajectory offers another clue. By backtracking its path, astronomers have pinpointed possible ejection sites, though no single cluster definitively claims it yet. The uncertainty adds to the mystery. Could this black hole have been expelled from a now disrupted dwarf galaxy? Or was its birthplace a globular cluster that since dissolved into the Milky Way's halo? The physics behind its velocity is just as compelling. For a black hole to reach 400 kilometers per second, the ejection event must have transferred staggering energy equivalent to detonating 1 million supernovae simultaneously in precisely coordinated directions. That's the level of precision only nature's most extreme gravitational interactions can achieve. Yet despite this violence, the black hole held onto its stellar companion, a testament to the bond even gravity's outlaws can maintain. Now adrift in the galactic hinterlands, XT Joan 118 plus 480 faces an uncertain future. Most rogue black holes wander alone, but this one's persistent stellar partnership allows continued study. As it plows through the Milky Way's sparse outer regions, it may eventually collide with a molecular cloud, sparking new X-ray flares, or perhaps encounter another star system, triggering another round of gravitational chaos. Until then, it serves as a reminder that even the universe's darkest objects can't escape the consequences of cosmic bar fights, and sometimes the losers get the most interesting stories. Some stars don't just spin, they pirouette at speeds that defy physics as we know it. VFTS 102, a massive young star in the Tarantula Nebula, whips around so fast its equator streaks through space at 600 kilometers per second faster than most fighter jets cross the sky. At that dizzying velocity, its surface completes a full rotation every 25 hours, while a similar star like our Sun takes nearly a month. The forces at play here are extreme enough to stretch the star into an oblate shape, wider at the equator than the poles, like a cosmic spinning top deformed by its own motion. What makes this stellar speedster truly fascinating is its violent backstory. VFTS 102 likely didn't start life spinning this fast. It was almost certainly spun up by a catastrophic cosmic tango. The prevailing theory suggests it once orbited in a binary system with another massive star. When its partner went supernova, the sudden release from gravitational bonds and the explosive kick from the detonation could have sent VFTS 102 whirling like a figure skater pulling in their arms mid-spin. The numbers are staggering. The energy required to accelerate such a massive object to these speeds exceeds the total output of 1 million nuclear bombs detonating simultaneously. The evidence supporting this scenario lies in the star's surroundings. VFTS 102 isn't alone in its high-speed drama. It's accompanied by a runaway pulsar, a neutron star fleeing the scene at over 150 kilometers per second. Measurements show these two objects are moving away from a common point in space, strongly suggesting they were once gravitationally bound before the supernova explosion sent them careening in opposite directions. It's a celestial crime scene, with the pulsar as the smoking gun and VFTS 102's extreme rotation as the lingering evidence of their violent separation. But surviving such trauma comes at a cost. The star's rapid spin creates an enormous equatorial bulge where surface gravity is significantly weaker, allowing massive amounts of stellar material to escape into space. Observations reveal a thick disk of ejected gas encircling VFTS 102's midsection, a glowing cosmic hula hoop of superheated plasma. This stellar exhaust carries away angular momentum, gradually slowing the star's rotation over time. Even so, at its current rate, VFTS 102 will keep spinning wildly for millions of years before settling down to more sedate rotation speeds. The star's extreme environment adds another layer of intrigue. Nestled within the Tarantula Nebula, one of the most active star-forming regions in our galactic neighborhood, VFTS 102 is surrounded by young, massive stars that could potentially influence its fate. Some theories suggest gravitational interactions with these neighbors might eventually destabilize its rotation further, possibly triggering additional mass ejection or even premature stellar collapse. Others propose its rapid spin might protect it from certain types of stellar instability by maintaining internal circulation patterns that more sedentary stars lack. What makes VFTS 102 particularly valuable to astronomers is its role as a natural laboratory for stellar physics. Stars rotating this fast are rare, offering glimpses into behaviors that challenge our standard models of stellar evolution. Its surface temperature variations hotter at the poles where gravity is stronger and material, compressors more tightly provide real-world data to test theories about how rotation affects energy distribution in massive stars. The chemical composition of its ejected disk offers insights into how rapidly rotating stars enrich their surroundings with heavy elements. Perhaps most remarkably, VFTS 102 represents a fleeting phase in stellar existence. Few stars maintain such extreme rotation for long before either shedding the excess angular momentum or meeting a violent end. Those that do often become progenitors of unusual supernova or gamma-ray bursts, their rapid spins channeling their death throws into focused jets of energy rather than spherical explosions. Some may even collapse directly into black holes without the traditional supernova fireworks, their immense rotational energy funneled into powering relativistic jets instead. For now, VFTS 102 continues its frenetic dance through the Tarantula Nebula, a shining example of how cosmic violence can transform ordinary stars into record-breaking phenomena. Its existence reminds us that the universe has ways of spinning objects up to speeds we once thought impossible, creating natural marvels that challenge our understanding of physics while painting the cosmos with spectacular displays of celestial motion. Galactic collisions aren't just spectacular light shows, they're cosmic catapults capable of launching stars across the universe at unimaginable speeds. When galaxies like those in the Virgo cluster slam together, their gravitational chaos doesn't merely rearrange stars, it flings them outward like cosmic shrapnel at 3,000 kilometers per second, fast enough to cross the entire Milky Way in just 1 million years. These hypervelocity ejecta aren't lone wanderers. They form vast, luminous rivers of stars stretching hundreds of thousands of light-years, ghostly reminders of the violence that birthed them. Take the star stream trailing from galaxy M87 in Virgo, a shimmering arc of exiled suns hurtling through space with enough collective energy to outshine small galaxies. These stars didn't slowly drift away. They were violently ejected during M87's ancient merger with a smaller galaxy, slingshotted by the supermassive black hole's gravitational pull as it devoured its companion. The physics at play is staggering. As two black holes spiral toward merger, their gravitational dance flings nearby stars outward with such force they escape the galaxy's grip entirely. Imagine a celestial billiard shot where the cue ball is a supermassive black hole, and the scattered balls are stars fired across intergalactic space. What makes these streams so valuable to astronomers isn't just their speed, it's the story they tell about galactic evolution. Unlike globular clusters or dwarf galaxies, hypervelocity streams retain the chemical fingerprints of their home galaxies. By analyzing their starlight, scientists can reconstruct the merger that created them, like paleontologists reading fossils. The stars in M87 stream, for example, contain higher proportions of heavy elements than typical intergalactic stars, revealing they originated near the galaxy's metal-rich core before being violently ejected. These streams also serve as cosmic measuring tapes. Their shapes and speeds let astronomers calculate the mass of the galaxies that launched them, including the invisible dark matter that comprises most of a galaxy's gravitational pull. When a star gets flung outward at 3,000 kilometers per second, that velocity encodes information about the depth of the galactic gravity well it escaped. Recent studies of Virgo streams suggest some galaxies there contain 50 times more dark matter than visible stars, a ratio that challenges existing models of galaxy formation. The aftermath of these ejections reshapes entire galaxy clusters. Hypervelocity stars act as intergalactic probes, heating the sparse gas between galaxies as they plow through it at breakneck speeds. Some even carry planets with them, worlds ripped from their original orbits and now adrift in the void, lit only by the fading glow of their exiled suns. Over billions of years, these streams will disperse, their stars blending into the cluster's halo. But for now, they streak through the cosmos as luminous scars, reminders that even the grandest structures in the universe are subject to the chaos of gravitational collisions. One of the most astonishing discoveries is how long these streams endure. Unlike tidal tails, which fade as their stars disperse, hypervelocity streams maintain coherence for billions of years, their stars moving in near parallel trajectories like cosmic bullets frozen mid-flight. This persistence allows astronomers to trace mergers that occurred when the universe was half its current age, offering glimpses into how galaxy clusters assembled over cosmic time. The next generation of telescopes promises to uncover even faster ejecta, stars possibly accelerated to 1% light speed during collisions between supermassive black holes. These extreme velocities could carry stars clear out of their galaxy clusters, launching them on trajectories that will take them across the observable universe. It's a humbling thought. Some stars we see today might already be intergalactic voyagers, their origins lost to time but their speed eternally etching their stories across the sky. Deep in the constellation Cygnus, a newborn star barely 1/10 the Sun's mass is already flexing cosmic muscles, launching jets of molecular gas at 200 kilometers per second, fast enough to cross Earth's diameter in under a minute. This protostellar powerhouse, known as ERA's 20126 plus 4104, defies expectations by proving even stellar infants can generate outflows rivaling those of their massive evolved siblings. What makes this molecular hurricane extraordinary isn't just its speed. It's the precision with which it carves through its stellar nursery, sculpting the surrounding gas into intricate shock patterns visible across light years. The mechanics behind this jet reveal nature's ingenuity. As the protostar gathers mass from its surrounding disk, magnetic fields channel some of the infalling material into bipolar jets, cosmic fire hoses aligned with the star's rotational axis. Unlike the diffuse winds of older stars, ERA's 20126's outflow consists of dense molecular clumps, primarily carbon monoxide and water vapor, hurled outward with enough force to plow through interstellar clouds like a bulldozer through fog. These aren't gentle stellar breezes, they're hypersonic avalanches. Their energy so concentrated they create bow shocks where they collide with slower moving gas, heating it to thousands of degrees. Observations from radio telescopes capture the outflow's structure in stunning detail. Twin beams extend over 20,000 astronomical units, 300 billion kilometers each, their tips glowing with methanol masers, natural microwave lasers created by excited molecules. The jet's spine shows periodic knots like beads on a string, marking where the protostar's engine has pulsed with bursts of increased activity. These variations suggest the star's growth isn't steady but occurs in fits and starts, each feeding frenzy launching a fresh volley of high-speed gas. What's truly astonishing is how such a young, low-mass object generates this violence. Typically, only massive protostars produce extreme outflows, their intense radiation and magnetic fields easily overpowering gravity. ERA's 20126 challenges that assumption. Its luminosity is modest, yet its jets pack energy comparable to a supernova's first hour, just focused into narrow streams. The secret may lie in its unusually strong magnetic field, which acts like a cosmic particle accelerator, slinging material outward along tightly collimated paths. The outflow's impact on its environment is equally dramatic. By blasting away surrounding gas, it prevents the protostar from growing too large too quickly, a self-regulating mechanism that might explain why most stars in the universe are small. Meanwhile, the jet's shock waves compress nearby gas clouds, triggering secondary star formation like dominoes falling in its wake. This dual role, destroying potential stellar fuel in one region while seeding it in another, makes ERA's 20126 a microcosm of the feedback cycles that shape entire galaxies. Perhaps most intriguing is what this system reveals about our own solar system's infancy. Similar molecular outflows likely surrounded the young sun, their furious winds scattering the primordial nebula and influencing the arrangement of planets. Some theories even suggest these jets delivered water-rich material to Earth's vicinity. Their high speed impacts chemically altering the building blocks of terrestrial worlds. In that sense, ERA's 20126 offers more than just a cosmic speed record. It's a window into the chaotic nursery where every star, including our own, began its life. When a star ventures too close to a supermassive black hole, it doesn't just vanish quietly, it puts on one of the universe's most violent light shows. Tidal disruption events rip stars apart with such ferocity that their remains become relativistic plasma jets, screaming outward at 30,000 kilometers per second, 10% the speed of light. This isn't just destruction, it's transformation on a cosmic scale where gravity's grip converts an entire star's worth of matter into a high-energy particle beam visible across the universe. The physics behind these extreme speeds begins with spaghettification, the black hole's tidal forces stretching the star into a thin, hot stream of plasma as it crosses the event horizon. But here's where it gets wild. Not all that material falls in. Some gets whipped around the black hole's poles by magnetic fields trillions of times stronger than Earth's, funneled into twin jets that blast through space like cosmic blowtorches. The energy release is staggering, equivalent to detonating 1 billion hydrogen bombs every millisecond, focused into beams narrower than our solar system. Take the event catalogued as a SASSN-14 Li, where a sun-like star was torn apart by a black hole 20 million times more massive than our sun. As the stellar debris spiraled inward, shock waves heated it to hundreds of millions of degrees, creating an X-ray flare brighter than the host galaxy's combined starlight. But the real spectacle emerged weeks later. Radio telescopes detected jets moving at relativistic speeds, their synchrotron glow revealing electrons spiraling along magnetic field lines at near-light velocities. These weren't just random emissions, they were the dying star's material, recycled into nature's most powerful particle accelerator. What makes these jets so valuable to astronomers is their diagnostic power. Their speed and structure encode information about the black hole's spin, a property otherwise nearly impossible to measure. Faster spins produce more tightly collimated jets, while the plasma's composition hints at the original star's chemistry. In 2018, observations of tidal disruption event, a T2019 DSG, revealed something even more surprising. The jets flickered in brightness every 2 weeks, suggesting the black hole was processing like a wobbly top as it devoured the star. Yet the most dramatic effects occur at the particle level. Atoms torn apart in the disruption get rebuilt under extreme conditions, forging heavy elements like gold and platinum in seconds, a process that normally takes supernova days. These freshly minted metals join the jet's high-speed exodus, meaning tidal disruption events don't just destroy stars, they scatter their enriched remains across intergalactic space at velocities that could carry them clear out of galaxy clusters. The aftermath is equally spectacular. As the jets plow through interstellar gas, they create expanding bubbles of multi-million-degree plasma visible for millennia. Some even generate coherent radio waves, cosmic lasers on galactic scales that pulse with clockwork regularity. These relics allow astronomers to reconstruct ancient disruption events long after the initial flare fades, like forensic scientists analyzing a stellar crime scene billions of years cold. What's truly humbling is realizing these events aren't rare. Current estimates suggest every galaxy experiences a tidal disruption roughly every 10,000 years. Our own Milky Way may be overdue for such a spectacle, with Sagittarius, a star lurking quietly at its core. When it next feeds, the resulting jets could outshine the full moon in X-rays, a silent reminder that even in apparent stillness, the universe reserves its most extreme velocities for moments of catastrophic transformation. Most galaxies rotate like slow, graceful whirlpools, but not ESO 510-G13. This cosmic oddball spins so fast its central bar, a dense structure of stars stretching 40,000 light-years, whirls at 300 kilometers per second, fast enough to cross Earth's entire diameter in under 40 seconds. What makes this galactic speedster truly bizarre isn't just its velocity, it's the way its entire disk bends like a warped vinyl record, twisted by forces we're only beginning to understand. The galactic bar at ESO 510-G13's heart acts like a colossal stellar mixer, channeling vast amounts of gas toward the galaxy's core at breakneck speeds. Picture an Olympic hammer thrower spinning with a cable stretching thousands of light years, except instead of a metal ball, it's billions of stars moving in eerie synchronization. This rapid motion generates shock waves that compress interstellar gas, triggering violent bursts of star formation along the bar's leading edges. Infrared telescopes reveal the aftermath, ribbons of newborn stars glowing like cosmic fireworks frozen mid-explosion. What sets this galaxy apart is the visible toll such extreme rotation takes on its structure. Unlike the flat, orderly disks of most spirals, ESO 510-G13's outer regions curve dramatically upward at the edges, the astronomical equivalent of a pizza crust warping in a cosmic oven. The leading theory suggests a recent close encounter with another galaxy twisted it into this peculiar shape, the gravitational interaction simultaneously transferring enough angular momentum to rev its central bar to unprecedented speeds. The galaxy's frenetic environment offers clues about how bars influence galactic evolution. Normally, these structures gradually slow as they age, their rotation braked by dynamical friction with dark matter halos. ESO 510-G13 defies this pattern. Its bar shows no signs of slowing, possibly because fresh gas inflows from the distorted disk continually replenish its momentum. This creates a self-sustaining cycle. The bar's rotation drives gas inward, forming new stars whose explosive deaths later pump energy back into the system. Spectroscopic observations reveal another oddity. While the bar rotates as a solid block, the outer disk lags behind, creating shear forces that stretch star clusters into smears of light. This velocity mismatch may explain the galaxy's unusually high rate of hypervelocity stars, lone suns flung clear of their birthplaces by gravitational slingshots near the rapidly spinning bar. Some of these stellar outcasts reach escape velocity, destined to drift forever in intergalactic space. The most tantalizing question is what happens next. Models suggest such extreme rotation could eventually destabilize the bar, causing it to buckle vertically or even dissolve into a more chaotic structure. Alternatively, the constant gas influx might fuel the growth of an active galactic nucleus, transforming ESO 510-G13 into a quasar. For now, it remains a cosmic laboratory, a rare glimpse into how galaxies push their rotational limits, bending but never quite breaking under forces that would shred lesser structures. Globular clusters usually orbit their galaxies like bees around a hive, slow, ancient, and predictable. But HVGC1 is different. This rogue star city barrels through intergalactic space at 3 million kilometers per hour, fast enough to cross the distance from Earth to the Moon in less than half a second. Its staggering velocity isn't just unusual. It's evidence of a gravitational slingshot so powerful it defies conventional models of galactic dynamics. The story of HVGC1's escape begins in the chaotic core of Messier 87, a giant elliptical galaxy anchoring the Virgo cluster. When two supermassive black holes spiraled toward merger, their gravitational dance created a cosmic catapult effect. As HVGC1 passed too close to this binary black hole system, the complex interplay of forces flung it outward like a stone from a trebuchet, except in this case, the stone was a dense sphere containing nearly 1 million stars packed into just 30 light-years of space. The energy required to accelerate such a massive object to this speed, is almost inconceivable, equivalent to the simultaneous explosion of 10,000 supernova focused into a single directional kick. What makes hypervelocity globular clusters especially valuable to astronomers is their composition. Unlike solitary hypervelocity stars, which often get torn apart during ejection, globular clusters retain their structure, allowing scientists to study pristine stellar populations that have remained chemically unchanged since their violent expulsion. HVGC-1 stars act like cosmic historians, their metallicity and age distribution revealing it was likely torn from M87's central regions, where star formation occurred earlier and more intensely than in the galaxy's outskirts. The aftermath of this ejection paints an even more dramatic picture. As HVGC-1 streaks through intergalactic space, it leaves a subtle trail, not of glowing gas, but of stripped stars gradually peeling away from its outer edges due to tidal forces. These stellar escapees form faint streams barely detectable with current telescopes, marking the cluster's path like breadcrumbs across the cosmic dark. Meanwhile, the cluster's core remains remarkably intact, its stars held together by mutual gravity despite moving fast enough to escape the pull of any known galaxy. Astronomers suspect HVGC-1 isn't alone. Surveys suggest dozens of similar runaway clusters may be racing unseen through galaxy clusters, their high speeds making them challenging to detect. Some could be intergalactic interlopers, having traveled so far they no longer bear any chemical resemblance to the galaxies they once called home. Others might eventually collide with new host galaxies, their stars assimilating into foreign stellar populations like cosmic immigrants. The implications rewrite our understanding of globular clusters' role in galactic evolution. Once considered mere galactic satellites, these objects now appear capable of traversing vast intergalactic distances, potentially transporting heavy elements and even rogue planets between galaxies. HVGC-1's journey proves that the universe doesn't just accelerate individual stars, it can launch entire star clusters on trajectories that will take them beyond the reach of any galaxy's gravity, turning them into permanent wanderers of the cosmic void. Most stars drift through the galaxy at a leisurely pace, but white dwarf US 708 isn't just breaking speed records, it's practically rewriting the rulebook on stellar escape velocity. Clocked at a staggering 1,200 kilometers per second, this cosmic runaway moves fast enough to traverse the entire continental United States in just 3 seconds. To put that in perspective, if you could hitch a ride on this stellar speed demon, you'd outpace every known object in our solar system by a factor of over 100. The story behind this white dwarf's extreme velocity reads like a cosmic crime scene investigation. Unlike hypervelocity stars ejected by supermassive black holes, US 708 owes its speed to a far more violent origin: the thermonuclear detonation of its binary companion in a Type Ia supernova. Here's how the celestial mechanics played out. This white dwarf was once part of a stellar duo, siphoning material from its partner until it reached critical mass. When the stolen matter triggered a runaway fusion reaction, the resulting explosion didn't just obliterate the system, it launched the surviving white dwarf like a cosmic bullet from the blast. What makes US 708 particularly fascinating is the precision with which astronomers have reconstructed its trajectory. By analyzing its motion through the Milky Way's halo and comparing it to known supernova remnants, researchers traced its path back to a region near the constellation Hydra approximately 40 million years ago. The energy required to accelerate a stellar remnant weighing half our sun's mass to such ludicrous speeds is mind-bending, equivalent to converting the entire mass of Mount Everest directly into kinetic energy. This white dwarf's composition tells an equally compelling tale. Spectroscopy reveals an unusually high concentration of heavy metals like silicon and iron, the nuclear ash typical of Type Ia explosions. These elements aren't just surface contaminants, they're baked deep into US 708's atmosphere, suggesting the supernova's shockwaves may have partially engulfed the surviving star during its violent escape. The detection of these metals supports theories that some white dwarfs can weather nearby supernova without being completely vaporized, emerging instead as scorched high-velocity survivors. The implications of this discovery ripple far beyond one rogue star. US 708 serves as living proof that Type Ia supernova, already crucial as cosmic distance markers, can also function as nature's most powerful slingshots. Its existence suggests there could be thousands of similar supernova survivors racing unseen through our galaxy's halo, each carrying chemical fingerprints of their explosive past. Some might even bear traces of exotic elements created in the supernova's extreme conditions that we've yet to identify in laboratory settings. Looking to the future, this speedster's trajectory spells an inevitable exile. Unlike stars merely orbiting the Milky Way center, US 708 moves fast enough to escape our galaxy's gravitational pull entirely. Within another 100 million years, it will likely become an intergalactic wanderer, a lone stellar relic drifting through the void between galaxies. The same explosion that gave it this incredible speed also robbed it of any planetary companions, meaning its journey will be a solitary one through the cosmic dark. Yet, even as it flees, US 708 continues to surprise astronomers. Recent observations detected an unexpected ultraviolet glow around the white dwarf, possibly the last remnants of its supernova-heated outer layers or an accretion disk formed from interstellar material it's scooping up during its high-speed flight. Either way, this stellar fugitive proves that in the cosmos, even destruction can become a launch pad propelling survivors to velocities that defy imagination and sending them on journeys that will outlast the galaxies they once called home. Markarian 501 doesn't just shine its screams across the cosmos with a fury that defies belief. This blazar, a supermassive black hole tipped almost directly toward Earth, fires jets of plasma so energetic they outshine entire galaxies, their particles racing at 99.99% light speed. But what makes these relativistic jets truly extraordinary isn't just their velocity, it's how they act as natural particle accelerators, generating emissions so powerful they fluctuate enough to double or halve their brightness in mere minutes. The secret behind this cosmic violence lies in the blazar's structure. Like all active galaxies, Markarian 501's core houses a supermassive black hole devouring surrounding matter. As material spirals inward, friction heats it to billions of degrees, creating a magnetized plasma disk. But here's where blazars diverge. Their black holes channel part of this inferno into twin jets aligned almost perfectly with our line of sight. This alignment amplifies their emissions through relativistic beaming, a celestial optical illusion where particles moving near light speed appear brighter due to the compression of their light waves. The effect is like staring down the barrel of a cosmic flashlight with the beam dialed to oblivion. What's fascinating is how these jets accelerate particles to such extreme energies. Turbulent magnetic fields near the black hole's poles twist into helical coils, acting as electromagnetic slingshots. Protons and electrons caught in these fields don't just move quickly, they ricochet endlessly, gaining energy with each pass until they're hurled outward with enough force to escape the galaxy. Some reach energies 1,000,000 times beyond what humanity's largest colliders can produce, creating gamma rays so intense they briefly outshine the blazar's own jet in fleeting high-energy flares. Observing these jets is like watching a cosmic strobe light. In 2017, Markarian 501's gamma-ray emissions spiked so dramatically they saturated detectors on NASA's Fermi telescope. Follow-up studies revealed the cause, a shock wave propagating through the jet, compressing magnetic fields and supercharging particles like a tidal wave squeezing a spring. These events unfold over hours, not millennia, a testament to the dynamic chaos reigning near the black hole. the real mystery lies in the jet's composition. While electrons produce most of the visible synchrotron radiation, the highest energy gamma rays suggest protons are also being accelerated to near light speeds. These cosmic rays, if they reach Earth, can trigger particle showers in our atmosphere detectable by observatories like the Pierre-Auger array. By studying their patterns, scientists trace them back to blazars like Markarian 501 cosmic artillery firing subatomic bullets across billions of light years. Yet for all their ferocity, these jets are also strangely fragile. Millimeter-wave radio maps reveal knots of plasma that brighten and fade as they travel downstream, their paths kinked by instabilities that twist the jet like a writhing serpent. Some models suggest the black hole's spin pumps energy into these kinks, creating internal particle collisions that generate sudden flares. Other theories point to magnetic reconnection, a process where field lines snap and recombine, releasing energy like a cosmic short circuit. Markarian 501's greatest gift to astronomy might be its variability. Unlike more stable objects, its rapid brightness changes allow scientists to study jet physics in real time. A flare detected today might originate from an event just light days away from the black hole, practically next door in cosmic terms. This makes blazars unparalleled laboratories for probing Einstein's relativity under conditions no simulator could replicate. As we continue monitoring this high-speed maelstrom, each new observation peels back another layer of mystery, revealing a universe where black holes don't just consume, but also create, launching particles with energies that push the very limits of known physics. NGC 3201 isn't just another ancient star cluster slowly orbiting our galaxy. It's a cosmic fugitive tearing through space at 500 kilometers per second, fast enough to cross Earth's orbit in just 8 hours. What makes this globular cluster extraordinary isn't merely its speed, it's the trail of celestial breadcrumbs suggesting it wasn't born in the Milky Way at all, but was stolen from another galaxy billions of years ago. The evidence lies in its backward trajectory. Unlike most globular clusters placidly circling the galactic center, NGC 3201 barrels through the Milky Way's halo in a retrograde orbit, moving against the flow of our galaxy's rotation like a salmon swimming upstream. This peculiar motion, combined with its extreme velocity, marks it as an interloper from the cosmic neighborhood. Chemical analysis seals the case. Its stars contain distinct ratios of heavy elements that don't match the Milky Way's native clusters, bearing signatures more aligned with smaller satellite galaxies like the Sagittarius dwarf. Astronomers reconstruct its violent history through computer simulations. Somewhere between 10 and 12 billion years ago, when the Milky Way was still assembling itself, NGC 3201 likely belonged to a dwarf galaxy that strayed too close. As gravitational tides ripped the dwarf apart, the densely packed globular cluster survived the encounter intact but was sent careening through intergalactic space until our galaxy's gravity eventually captured it. The energy of that ancient collision still propels it today, making NGC 3201 a fossil record of the Milky Way's cannibalistic past. But speed isn't this cluster's only anomaly. Deep within its core lurks an invisible predator, a black hole approximately 4 times the Sun's mass, detected by the erratic orbits of surrounding stars. While most globular clusters have expelled their black holes through dynamical interactions, NGC 3201's retained predator suggests it formed under unusually dense conditions, perhaps in the chaotic environment of its original dwarf galaxy. This makes the cluster doubly valuable, a high-velocity time capsule preserving both galactic archaeology and exotic stellar dynamics. The cluster's current path only adds to its intrigue. Racing through the outer halo at nearly twice the velocity of similar objects, NGC 3201's trajectory will eventually slingshot it back toward the galactic outskirts. In about 200 million years, it will reach Galactic, the farthest point from the Milky Way's center before gravity pulls it back for another high-speed pass. Each orbit leaves it slightly more disrupted, with tidal forces slowly stripping away its outermost stars into a ghostly stream that traces its path across the sky. What's truly remarkable is how this speedster defies expectations of cluster survival. Conventional models suggest globular clusters moving this fast should have disintegrated long ago, torn apart by galactic tides. Yet NGC 3201 remains intact, its 100,000 stars bound together by gravity despite the violent forces acting upon them. This resilience hints at an incredibly dense core, so packed with stars that close encounters act as gravitational shock absorbers, stabilizing the cluster against external disruptions. Modern telescopes reveal another surprise. NGC 3201 contains an unusual population of blue stragglers, stars that appear younger than their neighbors despite the cluster's ancient age. These stellar anomalies likely formed through collisions or mass transfers between older stars, processes amplified by the cluster's crowded core. Their presence suggests high-speed environments like this may be stellar recycling factories, where old stars literally crash together to create new ones long after star formation should have ceased. As NGC 3201 continues its high-speed journey, it serves as a reminder that the Milky Way is no isolated island. It's a dynamic structure built from stolen stellar cities and cosmic collisions. This rogue cluster, along with a handful of others moving at similar velocities, represents the visible aftermath of our galaxy's growth through violent mergers. And somewhere out there, another intergalactic traveler might be hurtling toward us right now, destined to add its stars to the Milky Way's ever-changing tapestry. Most supernovae unfold with familiar, terrifying beauty, but SN 2002BJ broke all the rules when this stellar explosion lit up the galaxy NGC 1821 in 2002. Astronomers quickly realized they were witnessing something unprecedented, a supernova ejecting material at 20,000 kilometers per second, nearly 7% the speed of light. That's fast enough to cross Earth's entire diameter in under 2 seconds, a velocity so extreme it challenged everything we thought we knew about stellar deaths. What makes SN 2002BJ so baffling isn't just its speed. It's how quickly the whole spectacle played out. While typical supernovae brighten over weeks and fade over months, this cosmic oddball peaked in mere days before vanishing almost as abruptly as it appeared. The light curve resembled a flare more than an explosion, suggesting a fundamentally different mechanism at work. Spectroscopic analysis revealed the smoking gun, an unusual abundance of helium and intermediate mass elements like vanadium and chromium, signatures pointing to a theoretical but rarely observed phenomenon called a Ia or .1a supernova. Here's why this matters. Most type Ia supernovae occur when white dwarfs steal enough mass from companions to trigger carbon detonation. SN 2002BJ, however, appears to have involved a helium shell detonation, a thinner, faster-burning layer of helium igniting atop the white dwarf rather than its carbon core. Picture lighting gasoline instead of charcoal. The explosion is far more rapid and violent, but shorter-lived. The result, a supernova that functions like a cosmic flashbulb, its helium-rich outer layers blasted outward at velocities normally seen only in neutron star collisions. The aftermath holds equally fascinating clues. Normally, supernova ejecta expand in roughly spherical shells, but SN 2002BJ's debris showed asymmetric patterns in follow-up observations, evidence that the detonation was lopsided, perhaps channeling material into focused jets. This helps explain the extreme speeds. When an explosion isn't evenly distributed, the force gets concentrated, launching some fragments faster than others. The helium likely came from a companion star, its outer layers ripped away and compressed into an unstable shell before detonating like a stellar landmine. Yet the real mystery is how rare these events seem to be. Despite extensive supernova surveys, fewer than a dozen candidates matching SN 2002Bj's profile have been identified. This scarcity suggests the conditions required: a white dwarf with just the right thickness of helium shell, orbiting a helium-rich donor star at precisely the right distance, are cosmic rarities. It's possible most such explosions occur in galactic regions too dusty for easy detection, their brief flashes hidden behind interstellar veils. The implications stretch far beyond one peculiar supernova. If helium detonations are indeed responsible, they could produce significant amounts of unusual isotopes like titanium-44 and calcium-48, elements crucial for understanding nucleosynthesis in the universe. These high-speed ejecta also act as cosmic delivery systems, scattering freshly forged elements across interstellar space at velocities that allow them to penetrate regions normal supernova debris couldn't reach. Some models even suggest these events might leave behind partially intact white dwarfs, stellar survivors that could undergo multiple such explosions over their lifetimes. For astronomers, SN 2002Bj remains both a puzzle and a revelation, proof that the universe still harbors explosive phenomena that defy textbook explanations. Its extreme speed and bizarre chemistry make it a Rosetta Stone for understanding the diversity of stellar deaths, while its fleeting brilliance serves as a reminder that some of the cosmos' most extraordinary events might be over before we even realize what we're seeing. Imagine an explosion so violently lopsided it turns a dying star into a high-speed cosmic wrecking ball. That's exactly what happened with G292.0 plus 1.8. A supernova remnant hurtling through interstellar space at 600 kilometers per second, fast enough to cross the distance from Earth to the Moon in just 10 hours. This celestial speed demon isn't just drifting, it's carving a chaotic path through the galaxy, leaving behind a glowing trail of shock-heated gas and clues to one of nature's most unbalanced stellar deaths. The secret to this remnant's extreme velocity lies in its explosive birth. When the original massive star detonated roughly 3,000 years ago, the supernova wasn't symmetrical. More material blasted outward in one direction than the others. Picture a firecracker with half its powder packed tighter on one side. The resulting explosion would kick the remaining shell backward with tremendous force. In cosmic terms, that shell is the collapsed stellar core, now a neutron star, while the kick sends both the remnant and its pulsar fleeing in opposite directions at mind-bending speeds. Chandra X-ray observatory images revealed G292's aftermath in stunning detail. The debris field stretches over 30 light-years, its swirling tendrils of oxygen, neon, and silicon glowing like a celestial ink blot. But the smoking gun is the neutron star itself, displaced far from the explosion's geometric center, racing southwest at nearly the same speed as the expanding shockwave ahead of it. This mismatch proves the explosion's asymmetry wasn't subtle. It was catastrophic enough to effectively turn the supernova into a cosmic rocket engine. What makes this runaway remnant especially valuable to astronomers is its composition. Unlike most supernova debris, G292 is rich in intermediate mass elements like magnesium and silicon, the building blocks of rocky planets. These materials were forged in the star's final moments, then ejected at such high velocities they could eventually seed star-forming regions far from their birthplace. The remnant's motion creates a dynamic laboratory for studying how these heavy elements mix with interstellar gas, a process normally too slow to observe in real time. The physics behind this stellar propulsion system is just as fascinating. Current models suggest the neutrino emissions during collapse, normally symmetrical, may have been skewed by turbulent convection in the dying star's core. This imbalance created a neutrino rocket effect, where more of these ghostly particles streamed out one direction, nudging the newborn neutron star in the opposite direction through sheer momentum transfer. Combined with any pre-existing asymmetry in the star's outer layers, This could amplify kicks to the extreme velocities we observe. But G292 isn't the only remnant on the run. The pulsar B1508 plus 55 moves even faster at 1,100 kilometers per second, so rapid it's escaping the Milky Way entirely. Comparing these cosmic fugitives reveals a spectrum of supernova kicks, suggesting stellar deaths span a continuum from near-symmetrical collapses to violently off-center detonations. The outliers like G292 represent nature's most unbalanced explosions, where the laws of physics allow for staggering energy concentrations in specific directions. The long-term fate of these runaway remnants is just as dramatic. As G292 plows through interstellar space, its shock wave preheats and compresses gas ahead of it, potentially triggering new star formation in its wake like a cosmic snowplow piling up drifts. Meanwhile, the pulsar it left behind will continue its lonely journey, possibly becoming an intergalactic traveler if it maintains sufficient velocity to escape the galaxy's gravitational pull. Both objects carry chemical fingerprints of their explosive origin, time capsules preserving conditions from a stellar death 3 millennia past. What's truly humbling is realizing such events aren't rare, just rarely observed. For every G292 we spot, there may be dozens more whose trajectories don't conveniently point toward Earth. These high-speed remnants remind us that even in stellar death, the universe favors drama over decorum, transforming catastrophic explosions into engines that launch wreckage across the galaxy at speeds no human technology could ever hope to match. And somewhere out there, another massive star might be preparing for its own lopsided demise, ready to send its remnants racing through the cosmos on a high-velocity journey lasting millions of years. Deep in the constellation Aquila, a cosmic whirlpool defies the laws of physics. Jebris 1915 plus 105, a microquasar where plasma spirals into oblivion at half the speed of light. This isn't just rapid motion, it's space-time itself twisted into a frenzied dance, with superheated gas screaming toward a black hole 14 times heavier than our Sun. The accretion disk here isn't the orderly, slow-churning structure seen around most black holes. It's a maelstrom of ionized particles orbiting so fast that relativistic effects distort its very shape, stretching it into a glowing, lopsided oval under the black hole's relentless gravity. What makes this disk extraordinary isn't merely its speed, it's how that velocity reveals the extreme warping of space-time near the event horizon. As gas funnels inward, friction heats it to millions of degrees, emitting X-rays so intense they pulse with clock-like regularity. But here's where physics gets bizarre. The inner disk rotates so rapidly that time dilation becomes visible. To a distant observer, plasma near the edge appears to move slower than material deeper in, not because it's physically decelerating, but because the black hole's gravity stretches light's wavelength, creating a cosmic illusion where the laws of motion seem to bend. The microquasar's chaotic heartbeat offers further clues. Every 20 to 40 minutes, Jebris 1915 plus 105 erupts in violent oscillations, jets of plasma firing outward as the disk's inner edge periodically empties and refills. These eruptions aren't random. They're governed by hydrodynamics at relativistic speeds, where gas spiraling inward at 50% light speed suddenly hits a bottleneck, piling up until pressure overcomes gravity's grip. The resulting outbursts eject plasma bubbles that expand near light speed, visible as superluminal knots in radio telescopes. Magnetic fields add another layer of complexity. Chandra X-ray observatory data reveals the disk's plasma is threaded with magnetic coils tighter than any man-made solenoid. These fields don't just guide infalling material, they act like cosmic particle accelerators, boosting electrons to energies that emit gamma rays detectable across the galaxy. Some models suggest the disk's inner regions may harbor magnetic reconnection events akin to solar flares, but scaled up by factors of billions, generating sporadic bursts bright enough to outshine the disk itself. The real marvel is how such extreme physics remains measurable from 13,000 light-years away. Astronomers track the disk's rotation using ion emission lines, spectral fingerprints distorted by Doppler shifts as hot gas orbits the black hole. The lines smear asymmetrically, with one side stretched to redder wavelength gas moving away, and the other compressed to blue gas approaching. This skew reveals velocity gradients so steep they imply the disk's inner edge completes an orbit every second, while plasma mere kilometers outward takes minutes, a disparity only possible under gravity strong enough to twist space-time like taffy. GRS 1915 plus 105 isn't just a curiosity, it's a Rosetta Stone for understanding accretion physics across the cosmos. The same processes powering its disk, scaled up, drive quasars billions of times more luminous. Yet here, proximity allows us to observe details obscured in distant giants, from turbulence patterns to how magnetic fields channel energy into jets. Each X-ray fluctuation, each radio burst, carries encrypted data about how matter behaves under gravity's most extreme regimes, offering glimpses of universal laws that govern everything from stellar mass black holes to the supermassive monsters anchoring galaxies. This microquasar also poses unanswered questions. Why does its disk rotate faster than theoretical limits predict? What stabilizes its structure against centrifugal disintegration? The answers might lie in yet undetected physics, perhaps quantum effects near the event horizon or instabilities in plasma viscosity at relativistic speeds. For now, GRS 1915 plus 105 remains a cosmic laboratory, its hyperfast disk challenging our models while illuminating the wild frontier where Einstein's relativity and high-energy astrophysics collide. E04375439 isn't just fast, it's a cosmic fugitive that's already left its home galaxy behind. Hurtling through the void at nearly 3 million kilometers per hour, this hypervelocity star moves with such staggering momentum that the Milky Way's gravity can't hold it. By the time you finish reading this sentence, it will have traveled the distance from Earth to the Moon nearly twice over. But what makes this stellar outlaw truly remarkable isn't just its speed, it's the mystery of its origin, a celestial whodunit written in light and motion across millions of light-years. Most stars in the universe obediently orbit their galaxies, but E04375439 plays by different rules. Spectroscopic analysis reveals it's a young, blue star, just 100 million years old. Yet it's already deep in intergalactic space, far from any star-forming region. This paradox led astronomers to an astonishing conclusion. It was likely flung from the Large Magellanic Cloud, our galaxy's satellite, after a gravitational showdown between three massive stars. Here's how the cosmic physics unfolded in a densely packed stellar cluster. Three stars became locked in a chaotic dance. When one got too close to the pair, the gravitational slingshot effect ejected E04375439 at breakneck speed, while the other two merged or formed a tight binary. The energy behind this kick is mind-bending, equivalent to converting the entire mass of Mount Everest directly into kinetic energy focused onto a single stellar object. The evidence lies in the star's trajectory. By tracing its path backward through space, researchers found it aligns with the Large Magellanic Cloud's motion roughly 30 million years ago, the estimated time of its ejection. Even more compelling is its chemical fingerprint. The star's surface shows a higher ratio of heavy elements like oxygen and magnesium than typical Milky Way stars, matching the Magellanic Cloud's unique metallicity. Yet the lingering question remains, how did a star this young acquire enough velocity to escape its galaxy's grasp? Normally, such extreme speeds require interactions with supermassive black holes, but the Large Magellanic Cloud doesn't host one massive enough. This is where the three-body scenario shines. In dense stellar environments, complex gravitational interactions between multiple massive stars can produce ejections rivaling black hole slingshots. Simulations show that when 3 stars of 20 solar masses or more interact, the lightest often gets expelled at velocities exceeding the galaxy's escape speed. He0437 5439 fits this profile perfectly. Its mass 9 times the Sun's and age suggest it was the lightweight in a trio of stellar heavyweights. The expelled star's surface still bears scars of its violent departure, spectroscopic peculiarities hinting at a turbulent atmosphere, possibly stirred by shock waves from the ejection itself. What awaits this intergalactic traveler? Unlike stars merely orbiting the galactic center, He0437 5439 is on a one-way trip into the abyss. In another 50 million years, it will have traveled so far that even the combined gravity of the Milky Way and Andromeda galaxies won't be able to curve its path. It will become a true intergalactic wanderer, drifting through the darkness between galaxy clusters for billions of years. The irony is poignant: a young, hot star destined to spend eternity in the coldest, loneliest reaches of the universe, its brilliance visible only to civilizations with telescopes powerful enough to spot a single sun adrift in the cosmic ocean. Yet He0437 5439 journey isn't just a curiosity, it's a Rosetta Stone for understanding stellar dynamics. By studying its trajectory, astronomers have refined models of how stars can be ejected without black hole involvement. Its very existence proves that hypervelocity stars aren't exclusively products of galactic centers. They can also emerge from the chaotic nurseries of star clusters. This reshapes our understanding of how galaxies lose mass over time, as each high-speed escapee carries away not just stellar material, but also the potential for future planetary systems. The star also serves as a test subject for extreme astrophysics. Its isolation means its light reaches us nearly uncontaminated by interstellar gas, offering a pristine laboratory for studying stellar atmospheres. Some theories even suggest that stars like He0437 5439 might harbor rogue planets, worlds torn from their original orbits during the ejection, now frozen in eternal exile. While none have been detected yet, future telescopes might spot their subtle gravitational influence on the star's motion. As for its ultimate fate, the star will gradually cool over hundreds of millions of years, eventually becoming a white dwarf, but one unlike any in our galaxy. Untethered from any galactic system, it will drift until the cosmos itself evolves beyond recognition, a silent witness to the universe's expansion long after its birthplace has merged with other galaxies. He0437 5439 journey reminds us that the universe is far more dynamic and far more violent than it appears. Even the brightest stars can become cosmic castaways, hurled into the void by gravitational forces beyond comprehension, carrying their stories across the intergalactic deep. Deep within the Milky Way, a star corpse named SGR 1806-20 wakes from its slumber with a violence that briefly outshines our entire galaxy. This magnetar, a neutron star with a magnetic field a quadrillion times stronger than Earth's, doesn't just possess unimaginable power, it wields it with terrifying unpredictability. Every few decades, its crust buckles under magnetic stresses so extreme they rip spacetime itself, triggering relativistic flares that accelerate particles faster than any human-made collider ever could. The resulting explosion, lasting just a fraction of a second, unleashes more energy than our Sun emits in 150,000 years. The physics behind these cataclysms is both beautiful and terrifying. Magnetars like SGR 1806-20 are born spinning rapidly, their dizzying rotation winding magnetic field lines like cosmic rubber bands. Over millennia, these fields grow so strong they literally twist the star's solid iron crust. Yes, neutron stars have solid surfaces until it fractures like an overstressed spring. When the crust finally snaps, pent-up magnetic energy reconnects in a process called starquakes. launching electrons and positrons to 99.999% light speed in milliseconds. The acceleration is so sudden that particles experience forces equivalent to a baseball being flung from rest to 60 miles per hour in a trillionth of a second. December 27, 2004, offered humanity a front-row seat to this cosmic fireworks show. SGR 1806-20's flare bombarded Earth's upper atmosphere with enough gamma rays to ionize atoms 50,000 light-years away, an event so powerful it actually compressed our planet's magnetic field briefly. Satellites designed to detect nuclear weapon tests momentarily thought civilization was ending, their circuits overwhelmed by the magnetar's electromagnetic scream. What made this flare truly special was its light echo, X-rays bouncing off interstellar dust clouds, allowing astronomers to triangulate the explosion's mind-bending power, 500 quadrillion trillion watts, focused into a beam narrower than a pencil's width. These eruptions don't just break energy records, they warp fundamental physics. The flare's relativistic particles generate quantum electrodynamic effects usually seen only in particle accelerators, with electrons spiraling along magnetic field lines so tightly they emit synchrotron radiation across the entire electromagnetic spectrum. Some theories suggest the extreme conditions might even briefly produce electron-positron pairs from pure energy, recreating processes last common in the early universe. Meanwhile, the star's twisted magnetosphere acts like a cosmic particle collider, smashing ions together with such force they momentarily fuse into unstable elements that decay before reaching a billionth of a second. Yet for all their violence, magnetar flares serve a crucial cosmic purpose. The relativistic particles they eject seed interstellar space with high-energy cosmic rays, while their intense radiation may trigger chemical reactions in distant nebulas that eventually form life's building blocks. Some astronomers speculate that a nearby magnetar eruption in Earth's distant past could have influenced our planet's atmospheric chemistry, perhaps even triggering mutations that accelerated evolution. The most fascinating aspect, we've likely only seen these monsters in their gentle phase. Fossil records suggest Earth may have been struck by a magnetar blast 800 million years ago that stripped part of our ozone layer. And in distant galaxies, hyperflares thousands of times more powerful could explain mysterious phenomena like fast radio bursts. SGR 1806-20 and its kin remind us that the universe's most extreme particle accelerators aren't made in laboratories, they're forged in the depths of massive stars, lurking silently until their magnetic fury awakens to rewrite the rules of physics in fractions of a heartbeat. Hidden within the Orion Nebula, a cosmic newborn is flexing its stellar muscles in spectacular fashion. HH212, a protostar barely 100,000 years old, is already blasting twin jets of molecular gas across space at 300 kilometers per second, fast enough to cross the continental United States in just 12 seconds. These aren't gentle stellar breezes, they're hypersonic tsunamis of energy carving through the surrounding nebula with surgical precision, their shock fronts glowing brightly in infrared light as they collide with slower-moving interstellar material. What makes these jets extraordinary isn't just their speed, it's how perfectly symmetrical they are, stretching over 2.5 light-years in opposite directions like a cosmic tuning fork. Millimeter-wave telescopes reveal intricate patterns within the flow knots and bow shocks that mark periodic bursts of increased activity from the fledgling star. Each of these bright spots represents a clump of gas ejected with enough force to plow through interstellar clouds like a bullet through smoke, heating the surrounding hydrogen to thousands of degrees in the process. The youngest stars in the universe don't just form quietly, they announce their birth with these violent, high-speed outbursts. The mechanics behind this stellar tantrum reveal nature's ingenuity. As gas from the surrounding nebula spirals onto HH212's growing disk, powerful magnetic fields channel some of the infalling material into narrow jets aligned with the protostar's rotational axis. Think of it like water spiraling down a drain, except here the drain occasionally spits some of that water back out through twin fire hoses at hypersonic speeds. The process functions as a cosmic pressure release valve. Without these jets, the star would spin itself apart from all the angular momentum it's gathering. What's truly astonishing is how precisely astronomers can study this stellar infant. HH212's nearly edge on orientation gives us a perfect laboratory to measure jet speeds through Doppler shifts, the same principle that makes a siren's pitch change as it passes. The approaching jet shows spectral lines shifted toward blue wavelengths, while the receding counterpart glows redder, together forming a textbook demonstration of stellar kinematics. Meanwhile, the jet's composition, mostly carbon monoxide and water vapor, offers clues about chemistry in planet-forming regions, revealing how complex molecules survive the violent environment around young stars. The protostar's outflow leaves an indelible mark on its nursery. As the jets plow through surrounding gas, they create shock waves that compress nearby molecular clouds, potentially triggering the formation of additional stars in their wake. Some of the highest resolution images show the jets interacting with previously ejected material, creating glowing, wing-like structures that span the length of our solar system. These intricate patterns serve as cosmic fossil records, preserving the protostar's growth spurts like rings in a tree trunk. Yet for all their violence, HH212's jets play a crucial ecological role in stellar development. By clearing away excess gas, they prevent the young star from growing too massive too quickly, effectively regulating their own growth. They also enrich the surrounding interstellar medium with heavier elements, seeding future generations of stars and planets with the raw materials for rocky worlds. In a very real sense, these high-speed outflows are the universe's way of recycling stellar building blocks while maintaining balance in star-forming regions. As we continue observing HH212, each new discovery peels back another layer of mystery about how stars like our Sun began their lives. The protostar's perfect bipolar symmetry challenges theories about how magnetic fields shape young stellar systems, while its periodic outbursts offer glimpses into the chaotic feeding patterns of infant stars. Long after HH212 settles into main sequence adulthood, its high-speed jets will have left an enduring legacy, both in the glowing trails they've etched across space and in the secrets they've revealed about the dynamic processes that shape all stellar birth. Galaxies aren't just static collections of stars, they're dynamic engines breathing life into the cosmos through vast, high-speed gas cycles that would dwarf any terrestrial weather system. Imagine supernova explosions acting as cosmic pumps, launching massive geysers of hot gas outward at 200 kilometers per second, fast enough to cross Earth's orbit in less than a day. These aren't gentle flows, they're titanic fountains of ionized metal-rich material that blast hundreds of light-years above galactic disks before raining back down in shimmering curtains of cooling plasma, seeding future generations of stars with the heavy elements forged in stellar furnaces. The mechanics behind this galactic plumbing reveal nature's grand recycling scheme. When massive stars explode as supernova, their shock waves heat surrounding gas to millions of degrees, creating expanding bubbles that rupture through the galactic disk's cooler layers like champagne corks. X-ray telescopes capture these processes in action. Gigantic cavities in galaxies like NGC 3079, where superheated gas streams upward at velocities exceeding the escape speed of most planetary systems. What goes up must come down, though the journey isn't direct. As these metal-enriched geysers climb into the galactic halo, they gradually cool through radiation, condensing into dense clouds that eventually succumb to gravity's pull. The result, a cosmic version of the water cycle, where instead of raindrops, galaxies get showers of oxygen, carbon, and iron descending from their halos to enrich new stellar nurseries. One spectacular example lies in the Milky Way's own Fermi bubbles, twin lobes of hot gas stretching 25,000 light-years above and below our galactic center. These structures glow in gamma rays from high-speed particles, their very existence proving our galaxy's ongoing fountain activity. Spectroscopy reveals their composition, supernova ejecta mixed with interstellar gas, all moving with enough energy to punch through the galactic disk's magnetic barriers. But the real magic happens at the fountain's rainfall phase. Hubble observations of galaxies like NGC 891 show tendrils of cooler gas descending like celestial vines, their metallicity signatures matching elements produced in recent supernova explosions. These fountain flows aren't just beautiful, they're essential architects of galactic evolution. Without them, heavy elements would pool near star-forming regions, creating chemically oversaturated environments where future stars would form with radically different compositions. The fountains also regulate star formation itself. When too many supernovae erupt in quick succession, their combined outflows can actually shut down local star birth by blowing away the very gas required to make new suns. A self-regulating mechanism that prevents galaxies from burning through their fuel too quickly. The speed of these flows creates extraordinary phenomena. As fountain material plummets back into galactic disks at hypersonic velocities, it generates shock fronts that briefly outshine entire star clusters. In Galaxy M82, astronomers have clocked these cooling flows at 180 kilometers per second, their impacts triggering secondary star formation where they collide with disk gas. The energy dynamics are staggering. A single descending cloud can release as much kinetic energy upon landing as a supernova explosion, just spread out over a wider area and longer time frame. What makes galactic fountains truly humbling is their scale. A single fountain cycle can take hundreds of millions of years to complete, meaning the oxygen atoms in your last breath might have ridden these flows multiple times since the galaxy's youth. They connect all components of a galaxy, from the crowded stellar nurseries in spiral arms to the sparse halo regions where lone stars drift, in an endless cosmic dance of creation, destruction, and rebirth. And as telescopes peer deeper into nearby galaxies, we're finding these fountains aren't uniform. Some galaxies sport delicate filamentary flows like our Milky Way, while others exhibit violent geysers rocketing material clear out into intergalactic space, proving that even on galactic scales, nature abhors stagnation. Some stars don't just fade away, they go out with a supersonic scream. Take SDSS J1228+1040, a white dwarf whose stellar winds howl through space at 6,000 kilometers per second, fast enough to cross Earth's diameter in less than 2 seconds. These aren't ordinary stellar breezes, they're gale force ejections channeled and accelerated by magnetic fields 10,000 times stronger than Earth's, transforming a dying star's final breaths into one of nature's most powerful particle accelerators. What makes this system extraordinary is how it sculpts its own funeral shroud. The white dwarf's intense magnetic field, generated by currents in its degenerate matter, acts like a cosmic funnel, focusing the outgoing wind into an intricate spiral pattern visible in polarized light. Picture a garden sprinkler spinning at relativistic speeds, except instead of water, it's spraying ionized calcium and magnesium at 1/50th the speed of light. This whirling structure, observed via Doppler tomography, reveals wind velocities that increase dramatically near the magnetic poles, where field lines bunch together like strands of a twisted rope. The physics behind these extreme winds starts with the white dwarf's scorching surface temperature over 20,000 degrees Celsius. At these temperatures, intense ultraviolet radiation blasts atoms apart, creating a plasma of free electrons and ions. Normally, this material would expand outward evenly, but SDSS J1228's magnetic field changes everything. Charged particles get trapped along field lines, forced to spiral outward like beads on rotating wires. This magnetic confinement creates collimated jets at the poles while suppressing outflows near the equator, a stellar wind version of selective muting where only certain latitudes can scream into the void. Spectroscopic analysis uncovers even stranger details. The wind's composition shows unusual overabundances of heavy elements like titanium and chromium, metals that should have sunk beneath the white dwarf's surface due to their high atomic weight. Their presence suggests the magnetic field is so powerful it's dredging up material from deeper layers, like a cosmic blender churning the star's interior into its outflow. Some models even propose these fields create magnetic spots, analogous to sunspots but far more intense, where localized heating boosts wind velocities to their record-breaking extremes. The real fascination lies in how this system illuminates stellar life cycles. Most white dwarfs cool quietly over billions of years, but SDSS J1228 proves some remain dynamic long after nuclear fusion ends. Its winds carry enough kinetic energy to shape surrounding nebulosity for light years, creating shock fronts where they collide with interstellar gas. These interactions produce X-ray emissions detectable across the galaxy, turning what would normally be a dim stellar ember into a beacon of high-energy physics. Yet this white dwarf's most valuable gift might be its rarity. Of the 10,000 known white dwarfs, only a handful exhibit such extreme winds, making each one a precious laboratory for studying magnetohydrodynamics under conditions impossible to replicate on Earth. By tracking how these winds evolve over decades, astronomers can decode how magnetic fields decay in stellar corpses, a process that might eventually quiet SDSS J1228's furious gusts. Until then, it remains a testament to nature's ability to wring drama from even the quietest cosmic finales. Most stars drift through the galaxy in orderly fashion, but not Zeta Ophiuchi. This blue giant barrels through interstellar space at 400 kilometers per second, fast enough to cross Earth's orbit in just under an hour. Its reckless speed isn't just breaking cosmic traffic laws, it's sculpting a 20-light-year-long shockwave through surrounding gas clouds, visible in infrared as a glowing arc that could engulf 15 solar systems lined end-to-end. The secret to this stellar speedster's reckless motion lies in a violent breakup with a former companion. Zeta Ophiuchi once orbited an even more massive star until its partner went supernova. When that explosion tore the binary system apart, the sudden release of gravitational bonds sent the surviving blue giant careening through space like a cosmic pinball. The energy behind this kick is mind-bending equivalent to converting the entire mass of Mount Everest directly into kinetic energy, focused squarely on this single star. What makes Zeta Ophiuchi's journey spectacular isn't just its speed, it's the interstellar havoc left in its wake. As the star plows through surrounding gas clouds at supersonic velocities, it generates a bow shock analogous to the wave preceding a speedboat, only scaled up to interstellar proportions. The collision front heats gas to thousands of degrees, making it glow in infrared as dust particles get vaporized. NASA's WISE telescope captures this perfectly. A parabolic wall of compressed material expanding outward like a cosmic tsunami frozen mid-crash. The physics behind this structure reveals nature's artistry. Zeta Ophiuchi's powerful stellar wind blasting outward at 2,500 kilometers per second collides with slower-moving interstellar gas, creating a double shock system. First, the wind itself forms a termination shock where it suddenly slows. Then, the piled-up material forms a broader bow shock as it plows into undisturbed gas ahead. The result, a glowing, layered structure where different elements emit signature colors: oxygen-rich regions glowing blue while hydrogen molecules shine red. But here's what's truly astonishing. The shock's shape encodes the star's entire escape story. Asymmetries in the bow wave structure reveal Zeta Ophiuchi isn't moving perfectly upright relative to the galactic plane. It's angled about 30 degrees downward, suggesting its former binary orbit was inclined before the supernova blast sent it spinning into the void. The shock's brightness variations also map density fluctuations in the interstellar medium, acting like a cosmic sonar exposing invisible gas clouds. This runaway star's impact extends far beyond its glowing wake. The same shock waves that create its visible bow shock also trigger chemical reactions in surrounding molecular clouds. Ultraviolet radiation from Zeta Ophiuchus' surface, 20,000 times more intense than the Sun's, breaks apart simple molecules, allowing new, more complex compounds to form in the turbulent shock regions. Some astrochemists speculate such high-speed stellar intruders might be cosmic matchmakers, fostering conditions for organic molecule formation across the galaxy. Zeta Ophiuchus' future is just as dramatic as its past. In another few million years, a blink in cosmic time, it will likely encounter denser interstellar clouds that gradually slow its frenzied flight. Until then, it remains a blazing testament to the chaos lurking within seemingly orderly galactic neighborhoods, proof that even the most massive stars can become cosmic projectiles when stellar partnerships end in catastrophe. And somewhere out there, another runaway giant might be racing unseen through the void, preparing to carve its own glowing scar across the interstellar canvas. IGRJ 00291 plus 5934 isn't just another spinning neutron star. It's a cosmic siren devouring its companion with such ferocity that it briefly becomes the fastest accreting pulsar ever recorded. During its violent outbursts, this X-ray binary system transforms into a gravitational whirlpool, where matter stripped from a neighboring star spirals onto the pulsar's surface at 40,000 kilometers per second, over 13% the speed of light. That's fast enough to cross Earth's entire diameter in under 1 second, a velocity so extreme it warps the very fabric of space-time around the feeding frenzy. The mechanics behind this speed demon's appetite are as precise as they are violent. Locked in a tight orbit with a low-mass companion star, the pulsar's gravity relentlessly peels away layers of hydrogen-rich material, funneling it into an accretion disk that heats to millions of degrees. But here's where physics gets wild. The disk doesn't extend all the way to the neutron star's surface. Instead, it terminates abruptly where the pulsar's magnetic field becomes strong enough to overpower the inflowing gas's momentum. At this boundary, the material gets channeled along magnetic field lines like water down a cosmic drain, accelerating to relativistic speeds as it plunges toward the star's magnetic poles. What makes IGRJ 00291 plus 5934 truly exceptional is how it behaves during outbursts. Every few years, instabilities in the companion star's atmosphere trigger a dramatic increase in mass transfer. Think of a garden hose suddenly becoming a fire hose. As the accretion rate skyrockets, the pulsar's spin accelerates to nearly 600 rotations per second, its surface digesting the equivalent of one Mount Everest's worth of material every hour. X-ray telescopes capture these events as spectacular flares, the star's luminosity increasing 1,000-fold in just days. The energy release is so intense that it briefly outshines entire galaxies in high-energy wavelengths. The pulsar's breakneck rotation isn't just for show. It holds secrets about neutron star interiors. As matter impacts the surface at near light speeds, it creates hotspots that emit X-ray pulses with clockwork precision. By analyzing subtle timing variations in these pulses, astronomers have detected something astonishing: the star's crust flexing under the torrent of incoming material. These starquakes reveal that despite being just 20 kilometers wide, the neutron star's rigid crystalline crust floats atop a superfluid core, a bizarre state of matter where friction vanishes entirely. Yet the real marvel lies in the system's balancing act. Despite its periodic feeding frenzies, IGRJ 00291 plus 5934 never accumulates enough mass to collapse into a black hole. Each outburst is followed by a quiescent phase where the pulsar's powerful wind clears excess material, effectively hitting a cosmic reset button. This self-regulation makes it one of the most stable transient pulsars known, a paradox given its extreme behavior during eruptions. The implications ripple far beyond this single system. Pulsars like IGR J0029 1+5934 serve as natural laboratories for studying matter under conditions no Earth experiment could replicate. The magnetic fields near its surface trillions of times stronger than Earth's alter atomic structure so profoundly that atoms stretch into needle-like shapes. Meanwhile, the accretion process generates gravitational waves theoretically detectable across the galaxy, offering a potential new window into these high-energy phenomena. What's perhaps most fascinating is how transient such extreme states are. For most of its orbit, this system appears quiet, just another faint point of light. But when the conditions align, it transforms into a beacon of high-energy physics, reminding us that the universe reserves its most spectacular performances for those patient enough to watch and wait. And somewhere out there, another accreting pulsar might be preparing for its own record-breaking outburst. When gamma-ray bursts unleash the universe's most violent explosions, they don't just vanish into the void. Some leave behind neutron stars hurtling through space fast enough to cross entire galaxies in mere cosmic moments. These relativistic kicks occur when a collapsing star's death throws aren't perfectly symmetrical, creating an imbalance so extreme it rockets the newly formed neutron star away like a cosmic bullet. Imagine a cannon firing sideways, except here, the cannon is a dying star, and the recoil flings a city-sized stellar corpse at 1,000 kilometers per second. The physics behind these kicks starts deep within the collapsing star's core. As the star exhausts its nuclear fuel, its inner layers implode, rebounding into an inconceivably dense neutron star. But if more energy erupts from one hemisphere than the other, perhaps due to turbulent magnetic fields or asymmetric rotation, the conservation of momentum demands compensation. The result, the neutron star gets punted in the opposite direction with enough force to overcome its home galaxy's gravity. It's nature's version of Newton's third law, scaled up to cosmic extremes. For every burst of gamma rays fired into space, an equal and opposite thrust propels the stellar remnant into the void. These runaway neutron stars leave behind cryptic evidence of their escape. Without the star's continued energy input, the gamma-ray burst's afterglow fades abnormally fast, an orphaned remnant lacking the usual power source. Astronomers first spotted this phenomenon in JABI 160625b, where the fading X-ray afterglow drifted away from the explosion's epicenter at speeds matching theoretical kick predictions. The smoking gun, a faint, fast-moving X-ray source charting a path through interstellar space, the neutron star itself fleeing the scene of its catastrophic birth. What makes these kicks truly mind-bending are their relativistic effects. At such velocities, time for the neutron star slows noticeably compared to the surrounding universe, a real-world demonstration of Einstein's time dilation. A hypothetical observer riding on one of these stellar fugitives would age slightly slower than counterparts left behind. Meanwhile, the star's magnetic field gets stretched into an intense wake, potentially powering peculiar synchrotron trails visible in radio wavelengths, cosmic breadcrumbs marking its passage. Yet the implications stretch beyond mere stellar ballistics. These high-speed neutron stars act as celestial probes, their trajectories encoding secrets about their explosive origins. By reverse engineering their paths, astronomers can reconstruct the geometry of the original gamma-ray burst. Was it a narrow jet or a wider explosion? Did magnetic fields or neutrino emissions dominate the asymmetry? Each runaway carries clues in its velocity vector, a forensic fingerprint of the most violent event since the Big Bang. Some of these cosmic outlaws may even escape their galaxies entirely, becoming intergalactic wanderers drifting through the abyss between galaxy clusters. Over billions of years, their journeys could carry them far beyond the reach of any star system, lonely relics of ancient cataclysms, still glowing faintly with the heat of their traumatic births. Others might eventually collide with molecular clouds, their intense magnetic fields triggering new star formation in unlikely regions of space. The universe has countless ways to fling objects at unimaginable speeds, but relativistic kicks stand apart. They're not just about raw velocity, they're cosmic recoil written in starlight, proving that even in destruction, nature obeys strict accounting. Every directional burst of energy must be balanced by motion in the opposite direction, a fundamental symmetry playing out on scales that dwarf human comprehension. And somewhere out there, another gamma-ray burst might be preparing to launch its own stellar remnant into the cosmic darkness, setting it on a high-speed journey lasting billions of years. Somewhere in the black expanse between constellations Hydra and Centaurus, an invisible cosmic behemoth is rewriting the motion of our galactic neighborhood with irresistible gravitational force. The Great Attractor, an enigmatic gravitational anomaly, is pulling entire galaxy clusters toward it at speeds over 2 million kilometers per hour, a velocity so immense it would cross the distance from Earth to the Moon in less than half a second. This isn't just a few wandering galaxies. The local group containing our Milky Way, the Virgo supercluster, and hundreds of other galactic assemblies are all caught in this relentless current, part of a phenomenon astronomers call dark flow. What makes the Great Attractor so baffling isn't just its power, it's how effectively it hides from view. Nestled behind our galaxy's crowded disk in a zone astronomers call the zone of avoidance, its visible light is obscured by interstellar dust. We only know of its existence through indirect measurements, the subtle redshift patterns of galaxies revealing their coordinated movement toward a single point in space, like iron filings aligning toward a magnet we can't see. X-ray and radio telescopes have peeled back some of this cosmic curtain, revealing a concentration of mass equivalent to tens of thousands of Milky Ways packed into a region 600 million light-years across. The scale of this motion rewrites everything we thought we knew about cosmic structure. Normally, galaxies follow the Hubble flow, the general expansion of the universe that carries them apart over time. But the Great Attractor creates a glaring exception, overpowering this expansion on a local scale. Imagine floating in a gently widening river, only to find yourself and every nearby boat suddenly caught in a powerful undertow dragging you all toward a hidden whirlpool. That's the drama unfolding across our galactic neighborhood, with the Hydra-Centaurus supercluster at the center of this gravitational maelstrom. Recent surveys have uncovered an even more mind-bending twist. The Great Attractor itself appears to be moving, pulled toward something larger still. Dubbed the Shapley Attractor, this supercluster of galaxies 800 million light-years away may be the ultimate puppet master in our cosmic dance. Together, these titanic structures form part of the Laniakea supercluster, a web-like filament of galaxies stretching 500 million light-years, all streaming toward shared gravitational centers like water converging in a vast drainage basin. The implications ripple across cosmology. Such large-scale flows challenge models of how mass should be distributed in the universe, suggesting entire swaths of dark matter might be concentrated in ways we haven't yet accounted for. Some theories even speculate about exotic phenomena like cosmic strings, hypothetical defects in space-time structure, creating these megascale gravitational tugs. What's certain is that the Great Attractor's pull will shape our cosmic future over billions of years. The galaxies it's gathering may eventually merge into one of the largest structures in the observable universe. Yet for all its mystery, this gravitational giant offers a humbling perspective. We're not just observers of cosmic motion, but participants in it. Every star in our galaxy, including our Sun, is caught in this grand trajectory, swept along by forces more powerful than anything humanity could ever generate. It's a reminder that even in the vastness of space, no object moves in perfect isolation. Everything is connected through the invisible threads of gravity, woven into patterns we're only beginning to decipher. From stars flung at millions of miles per hour to black holes catapulted through galaxies, the universe operates on speeds that stretch our understanding of physics to its limits. Imagine hypervelocity stars racing fast enough to escape their galaxies entirely, or pulsars spinning hundreds of times per second, so rapid their surfaces near a quarter the speed of light. Picture gamma-ray bursts launching jets at 99.9999% light speed, creating cosmic illusions where matter appears to outpace light itself. These aren't just abstract numbers, they're real phenomena, forcing scientists to question how matter, energy, and space-time behave under conditions we can't replicate on Earth. Each extreme velocity we've explored serves as a natural laboratory. When neutron stars collide and fling debris at relativistic speeds, they reveal how heavy elements like gold are forged in cosmic collisions. Quasar winds tearing through galaxies at 40% light speed show how black holes shape entire galactic ecosystems. Even rogue planets drifting between stars, some accelerated by ancient supernovae, carry clues about the chaotic forces that sculpt star systems. These astronomical speed demons don't just break records, they break assumptions, testing Einstein's theories in environments where gravity warps time and particles reach energies 1,000,000 times beyond human-made accelerators. So which cosmic speedster left you stunned? Was it the runaway black hole fleeing its galaxy at 7 million kilometers per hour, dragging a 200,000 light-year trail of glowing gas? Or the oh my god particle, a lone proton from deep space that struck Earth's atmosphere at 99.9999999999% light speed, carrying energy equivalent to a baseball pitch in a subatomic package. Drop your favorite in the comments. We're still uncovering new extremes, and the universe always finds ways to surprise us. After all, the next record breaker might already be racing toward discovery, waiting to rewrite the rules once again.